The solar system consists of the Sun, 8 planets, their moons, and numerous smaller bodies such as asteroids, comets, and dwarf planets. For thousands of years, humans have studied it, beginning with Babylonian star charts inscribed on clay tablets and continuing to high-resolution images captured by modern spacecraft billions of kilometers away. Over time, new observations have shown that many long-held ideas about the solar system were oversimplified or incomplete. If you're curious about the surprising truths of our solar system and want to separate fact from fiction, subscribe now. Let's uncover the biggest myths you've been told about the planets and beyond. From the sizes of planets to the behavior of comets and the makeup of distant moons, many commonly accepted notions are misleading or outdated. In the following list, we highlight 27 of the biggest misconceptions about the solar system and explain what the evidence actually shows. The sun is not yellow. When you look up at the midday sky, the sun seems to blaze in a brilliant yellow-white, radiating warmth and light. This apparent color results from Earth's atmosphere. Step outside our planet's thin blue veil, and the sun appears as stark, intense white light. Seen from space, the sun doesn't glow yellow, orange, or red. It shines pure white, its light carrying the full spectrum of visible wavelengths almost equally. The reason we don't see that whiteness from Earth is Rayleigh scattering, the same process that makes our sky blue. As sunlight enters Earth's atmosphere, air molecules scatter shorter wavelengths, like blue and violet, more efficiently than longer ones like red and yellow. What remains when sunlight reaches our eyes from the sun's direction is slightly depleted in blue, giving the sun its soft yellowish hue. Astronomers classify the sun as a G2V main sequence star, which describes both its surface temperature and its place in the stellar life cycle. Its photosphere, the visible surface layer, burns at roughly 5,772 Kelvin, about 5,500 degrees Celsius. That temperature produces a spectrum of light that peaks in the green portion of visible wavelengths, around 500 nanometers. But since all colors are emitted with nearly equal intensity, they blend together as white. If you could float in space and look directly at the sun with proper protection, of course, you'd see not a yellow disk, but an intense white glare surrounded by faint coronal structures extending millions of kilometers outward. The sun's color matters far more than you might think. Its spectral profile, the distribution of light across wavelengths, defines how much energy reaches each planet. Climate scientists use precise solar data to model Earth's radiative balance, determining how energy from the sun drives weather, ocean currents, and the greenhouse effect. Solar engineers use the same data to calculate photovoltaic efficiency, the amount of power solar panels can convert from different wavelengths. If the sun were actually yellow, it would emit less blue and violet light, and our entire understanding of its energy output would shift. Spectroscopy, the science of analyzing light, first revealed the sun's true nature. In 1814, Joseph von Fraunhofer, a German physicist and optical lens maker, examined sunlight through a prism and discovered hundreds of dark lines crossing the spectrum now called Fraunhofer line. These absorption lines correspond to specific elements within the sun's atmosphere, including hydrogen, sodium, calcium, and iron. Today, modern instruments detect more than 25,000 such lines, allowing astronomers to determine the sun's composition with extraordinary precision. About 74% of its mass is hydrogen, 24% helium, and the remaining 2% includes heavier elements such as oxygen, carbon, and neon. Understanding how these elements interact with light helps explain variations in solar output. The sun experiences magnetic activity cycles lasting approximately 11 years, producing sunspots, solar flares, and coronal mass ejections, or CMEs. These phenomena cause small fluctuations in total solar irradiance, about 0.1% over a cycle, while sunspots appear as cooler dark patches and surrounding faculae emit more light, maintaining the overall output. Space observatories like SOHO, or SOLAR, and Heliospheric Observatory and SDO, or Solar Dynamics Observatory, continuously monitor these variations. Instruments aboard these spacecraft observe the Sun in multiple wavelengths, from visible to ultraviolet to extreme ultraviolet, revealing details invisible to human eyes. In ultraviolet light, for instance, the Sun's corona appears as a glowing halo of plasma at millions of degrees Kelvin, dramatically contrasting its calmer white light photosphere. The Sun's true color also changes subtly with perspective. When astronauts aboard the International Space Station film sunrises from orbit, the Sun appears stark white as it rises above the black curvature of Earth, before atmospheric scattering turns it golden as it meets the horizon. Similar white sunlight illuminates the Moon, which reflects it without altering its color, one reason the Moon appears grey and not yellowish when viewed from space. Educational illustrations often exaggerate the Sun's color to contrast it against a blue sky or depict heat visually. NASA imagery frequently uses false color processing to highlight features like magnetic fields or plasma temperatures. These methods help make data readable, but also affect how the Sun's color is perceived in popular media. The Sun's white light defines the range of visible wavelengths reaching Earth. When sunlight passes through Earth's atmosphere, oceans, and vegetation, it is absorbed, reflected, and scattered, producing the spectrum of blues, greens, and reds observed on the surface. If the Sun were cooler, as in a red dwarf, its peak emission would shift toward orange and infrared. If it were hotter, like a blue-white A-type star, ultraviolet output would increase. The current Sun emits a mix of visible and near-infrared light with a surface temperature of about 5,772 K. The Sun, as seen from Earth, appears yellow due to atmospheric scattering. Outside Earth's atmosphere, it emits white light. This white light drives Earth's climate systems, illuminates planetary bodies, and interacts with the surfaces of moons and distant objects in the solar system. Spacecraft observe the Sun as white light. Parker Solar Probe measures the solar corona, and Voyager 1, over 24 billion kilometers away, still detects its emission. The Sun is a fusion-powered star, emitting light that determines the spectral characteristics of objects throughout the solar system. The Sun isn't always calm. The Sun appears calm from Earth, but it is a highly dynamic star. Its activity ranges from subtle magnetic fluctuations to explosive events that can influence the solar system. Each second, the Sun emits approximately 3.8 times 10 to the power of 26 watts of energy, mostly as electromagnetic radiation, though this output is not perfectly uniform over time. Solar flares are sudden releases of electromagnetic energy from the Sun's atmosphere. They occur when magnetic field lines reconnect, releasing energy equivalent to millions of 100 megaton hydrogen bombs in minutes. Flares emit radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Those directed at Earth can interfere with satellite communications, GPS systems, and power grids. The GO satellites monitor solar X-ray emissions, with flare intensity classified from A class, the weakest, to X class, the strongest. The largest recorded flare, an X-28 flare in November 2003, saturated instruments and briefly affected radio communications in some regions. Coronal mass ejections are expulsions of plasma and magnetic fields from the Sun's outer atmosphere. A CME can contain billions of tons of ionized gas, traveling at speeds exceeding 3,000 kilometers per second. When a CME interacts with Earth's magnetosphere, it can trigger geomagnetic storms, induce electrical currents in power lines, and produce auroras visible at lower latitudes. The Carrington event of 1859 caused auroras as far south as Cuba, and telegraph operators reported sparks and some equipment fires. Sunspots are dark regions on the sun's surface, cooler than the surrounding photosphere, around 3,500, 4,500 degrees Celsius compared to 5,772 degrees Celsius. They form from concentrated magnetic flux that inhibits convection. Sunspots follow approximately 11-year cycles, from solar minimum to maximum and back. At solar maximum, sunspot numbers can exceed 100, while during solar minimum only a few may appear. Sunspots evolve, merge, and decay, occasionally triggering solar flares and CMEs. The Sun exhibits differential rotation, with the equator rotating approximately once every 25 days, and the poles taking about 36 days, which twists magnetic field lines and contributes to solar activity. Plasma flows, granulation patterns about the size of Texas, and bright points in ultraviolet light indicate small-scale magnetic reconnections. Observations from missions like SDO and Hinode document these plasma and magnetic phenomena across scales from hundreds of kilometers to millions. The Sun also produces a constant stream of particles known as the solar wind, primarily electrons and protons, which flow outward at speeds of 400–800 kilometers per second. This wind interacts with planetary magnetic fields and atmospheres, shaping the magnetospheres of planets like Earth, Jupiter, and Saturn. Comet tails, too, are sculpted by this flow of charged particles, with the ion tail always pointing away from the Sun, regardless of the comet's trajectory. Even at the edge of the solar system, the solar wind creates a vast bubble called the heliosphere, which shields the inner planets from the majority of galactic cosmic rays. Total solar irradiance, or TSI, fluctuates by about 0.1% over a solar cycle, influencing atmospheric chemistry, stratospheric temperature, and ozone distribution. High-energy particles from flares and CMEs pose radiation hazards to astronauts. Apollo missions accounted for potential solar particle events, and missions to Mars will require appropriate shielding. The Sun's corona reaches temperatures of 13 million Kelvin, hotter than the surface, and constantly sheds mass, heat, and magnetic energy into space. The Parker Solar Probe, launched in 2018, has approached within 7 million kilometers of the Sun to study magnetic fields and solar wind speeds directly. Jupiter's magnetosphere responds to the solar wind, generating auroras more energetic than Earth's. Mars, without a global magnetic field, experiences atmospheric stripping from high-energy solar particles. Saturn's rings, icy comets, and the atmospheres of distant moons are also affected by solar activity. The Sun produces X-class flares and experiences twisting magnetic field lines over decades, affecting the space environment around it. Sunscreen for planets. Planets in our solar system receive the Sun's energy in complex ways. Planets have shields and filters that affect how solar energy is absorbed, reflected, and redistributed, leading to a diversity of climates, surface conditions, and atmospheric chemistry. Mercury receives about 6.5 times the solar energy per square meter that Earth gets, averaging roughly 9,000 watts per square meter at noon on its equator. With almost no atmosphere, daytime temperatures exceed 430 degrees Celsius, while nights drop to nearly negative 180 degrees Celsius. NASA's MESSENGER mission mapped temperature fluctuations and showed that small topographical features can create microclimates. Venus, 108 million kilometers from the Sun, has a dense atmosphere of carbon dioxide with clouds of sulfuric acid. It receives about 2,600 watts per square meter, but the greenhouse effect traps heat, raising surface temperatures to around 465 degrees Celsius. Venus rotates slowly, taking 243 Earth days per rotation, producing a nearly uniform thermal profile. its clouds reflect about 70% of sunlight. ESA's Venus Express and NASA's Magellan missions observed super-rotating winds reaching 360 kilometers per hour in the upper atmosphere. Earth receives an average of 1,361 watts per square meter at the top of the atmosphere, but the energy reaching the surface varies with latitude, season, and cloud cover. The ozone layer absorbs ultraviolet radiation, while water vapor, carbon dioxide, and methane trap infrared radiation. Earth's axial tilt of 23.5 degrees produces seasonal variation. Clouds reflect sunlight and trap heat beneath. Ceres satellites measure that about 30% of incoming solar energy is reflected, while the rest is absorbed by the atmosphere, oceans, and land. Mars, 228 million kilometers from the Sun, receives about 43% of the solar energy Earth gets. Its thin atmosphere, mostly carbon dioxide at 0.6% of Earth's surface pressure, lets much of this energy reach the surface but retains little heat, creating temperature swings from -125 degrees Celsius at night to 20 degrees Celsius at the equator during midday. Orbiters like Mars Reconnaissance Orbiter and rovers such as Curiosity show how dust storms, polar ice caps, and seasonal CO2 sublimation affect sunlight absorption and reflection. Jupiter, 778 million kilometers from the Sun, receives about 3.7% of Earth's solar energy. Its massive atmosphere and magnetic field distribute energy across latitudes, producing cloud bands and storms. The Great Red Spot is partly powered by sunlight in the upper atmosphere and internal heat. Saturn, Uranus, and Neptune get 1%, 0.3%, and 0.1% of Earth's solar energy, respectively. Sunlight still drives upper atmosphere circulation, auroras, and seasonal changes. Cassini observations showed that Saturn's rings reflect sunlight, affecting moons like Enceladus, which emits water vapor plumes from both tidal heating and solar energy. Pluto, 5.9 billion kilometers from the Sun, receives about 0.06% of Earth's solar energy. Seasonal sublimation of surface ices occurs as Pluto approaches perihelion. New Horizons detected atmospheric changes caused by this solar energy. Comets, asteroids, and icy moons also experience sublimation, surface darkening, or color changes depending on solar exposure. The Sun's energy interacts with planetary magnetic fields. Earth's magnetosphere deflects charged solar wind particles, protecting the atmosphere, while Jupiter's magnetic field shields its moons. Mars, without a global magnetic field, has lost part of its atmosphere over billions of years due to solar and stellar particle interaction. Solar radiation is unevenly distributed across a planet. Day-night cycles, axial tilt, surface albedo, atmospheric composition, and cloud cover affect how energy is absorbed, reflected, or redirected. Satellites, probes, and surface missions account for these variations when planning power, instrumentation, and trajectories. The Sun's energy is filtered, reflected, absorbed, and redirected differently depending on a planet's atmosphere, magnetic field, rotation, and surface properties. These variations influence storms, climate, and atmospheric changes across the solar system. Mercury's hot side lie. Mercury, the closest planet to the Sun, has long been thought of as a world of extremes. One hemisphere scorched, the other frozen. Early astronomy often described it as a celestial grill beside an icy wasteland. This narrative influenced textbooks, documentaries, and popular understanding. Mercury does not, in fact, have a side permanently baked by the Sunday. Unlike the Moon, which exhibits a 1-to-1 tidal lock with Earth, Mercury rotates 3 times on its axis for every 2 orbits around the Sunday. This 3-to-2 spin-orbit resonance results in a rotation period of 58.6 Earth days, and an orbital period of 88 Earth days, confirmed definitively in 1965 through Earth-based radar observations by Gordon Pettengill and Rolf Dice at the Arecibo Observatory. This configuration produces an unusual day-night cycle. A solar day on Mercury, the time from one sunrise to the next, lasts 176 Earth days, meaning that any given point on the surface experiences long periods of light and dark, rather than eternal day or night. Temperature extremes on Mercury are large. Daytime temperatures can reach 430 degrees Celsius or 800 degrees Fahrenheit, while nighttime temperatures drop to 180 degrees Celsius or 290 degrees Fahrenheit. These swings occur because Mercury lacks a dense atmosphere to store heat. Mercury's exosphere, a thin layer of hydrogen, helium, sodium, and potassium, is too tenuous to retain heat. Each dawn and dusk brings rapid thermal changes. The myth of Mercury's locked face arose from observational limitations. Its close proximity to the Sun made telescopic tracking difficult. Early astronomers, including Giovanni Cassini, mistakenly thought Mercury was tidally locked. Radar astronomy in the mid-20th century overturned this assumption. Mercury's orbital eccentricity, 0.2056, makes it the most eccentric of the 8 major planets. At perihelion, 46 million kilometers, it receives about 2.5 times more solar flux than at aphelion, 69.8 million kilometers. This irregular input creates local variations in heating. Infrared measurements show regions near perihelion can exceed 430 degrees Celsius, while areas near aphelion may be slightly cooler. Modern spacecraft have revolutionized our understanding of Mercury. NASA's MESSENGER mission, also known as Mercury Surface, Space Environment, Geochemistry, and Ranging, which orbited the planet from 2011 to 2015, produced detailed maps of the entire surface. MESSENGER's imaging and spectroscopy revealed heavily cratered terrain, massive cliffs known as lobate scarps, and evidence of volcanic plains features indicating a dynamic geological history. The infrared spectrometer confirmed the presence of temperature variations across different latitudes and elevations, as well as permanent shadowed regions within craters near the poles. One of Mercury's most surprising discoveries is water ice in permanently shadowed craters. Radar observations from the 1,990 seconds confirmed by MESSENGER detected highly reflective regions above 85 degrees latitude, indicative of frozen water. Some deposits span tens of kilometers, preserved in perpetual darkness. Mercury's surface is a patchwork of extremes. Equatorial regions experience the most dramatic diurnal swings, while the poles remain comparatively stable due to permanent shadowing. Darker areas, rich in iron and magnesium-bearing minerals, absorb more sunlight and heat up more, whereas lighter regions reflect more energy and stay slightly cooler. MESSENGER data revealed complex interactions with the solar wind. Mercury's magnetic field, only about 1% as strong as Earth's, deflects charged particles toward the polar regions, producing auroral emissions. These interactions, along with the exosphere and thermal cycling, create a constantly evolving environment. Mercury's long-term evolution challenges earlier assumptions. Its high density, 5.427 grams per cubic centimeter, and large iron core, about 75% of its radius, affect internal heat distribution and may influence surface temperatures. Recent tectonic activity, inferred from lobate scarps less than 100 million years old, suggests the planet is still contracting slightly as it cools. Mercury's daytime heat is extreme but episodic. Long nights bring near absolute cold. Observations show that every region experiences both blistering heat and frigid cold during a single solar day. Venus isn't the hottest because of distance. Ask most people why Venus is the hottest planet in the solar system, and the immediate answer is usually because it's closer to the Sunday. Venus orbits at an average distance of 108 million kilometers from the Sun, closer than Earth's 150 million kilometers, but still farther than Mercury's 58 million kilometers. Mercury, despite being the closest planet, is cooler than Venus overall. Venus is wrapped in a dense, crushing atmosphere, about 90 times the surface pressure of Earth, comparable to the pressure experienced nearly 1 kilometer beneath Earth's oceans. Its composition is dominated by carbon dioxide, CO2, accounting for roughly 96.5% of the atmosphere, with nitrogen making up most of the remainder. Layers of reflective sulfuric acid clouds, concentrated between 45 and 70 kilometers above the surface, form an almost permanent blanket that scatters sunlight, giving Venus its bright yellow-white appearance in our sky. While these clouds reflect about 70% of incoming sunlight, enough solar energy penetrates to warm the surface. Once absorbed, heat is trapped by CO2 in an extreme greenhouse effect, elevating surface temperatures to a consistent 465 degrees Celsius or 869 degrees Fahrenheit. Venus is hotter than Mercury, despite being farther from the Sunday. Mercury's daytime highs of 430 degrees Celsius or 800 degrees Fahrenheit occur only in full sunlight and drop to 180 degrees Celsius or 290 degrees Fahrenheit at night due to its thin atmosphere. Venus's temperatures are remarkably uniform across latitudes and between day and night, rarely deviating by more than plus or minus 5 degrees Celsius. Venus's slow retrograde rotation adds another layer to its thermal uniformity. A single rotation takes 243 Earth days, meaning a Venusian day is longer than its year of 225 Earth days. Yet, unlike Mercury, which experiences drastic diurnal swings due to its thin atmosphere, Venus does not undergo extreme heating followed by freezing. Atmospheric winds, zonal superrotations traveling up to 360 km per hour at cloud top levels, redistribute energy efficiently from equator to poles and from the sunlit side to the night side, creating a globally even thermal profile. Our understanding of Venus's surface and temperature comes largely from the Soviet Venera missions in the 1970 seconds and 1980 second. Venera 7 in 1970 was the first spacecraft to transmit data from the surface, recording pressures of 90 atmospheres and temperatures above 475 degrees Celsius. Subsequent landers, Venera 9, 10, 13, and 14, confirmed these readings and returned images showing volcanic plains, boulder-strewn terrain, and sulfur-rich rocks. Venera 13 survived only 127 minutes, but sent back color photographs and chemical analyses, revealing basaltic rocks containing iron and magnesium. Venus's runaway greenhouse effect illustrates the planet-scale consequences of trapping heat. Solar energy passes through the upper atmosphere and warms the surface. That energy is then radiated as infrared radiation, which CO2 molecules absorb and re-emit, effectively trapping heat. Over geological time, this feedback loop may have eliminated any early oceans and maintained the planet's extreme temperatures for billions of years. Estimates suggest that the average surface temperature has remained near 465 degrees Celsius for at least 500 million years, long enough to prevent the condensation of water and the development of Earth-like climate cycles. Venus's cloud layer contributes to both reflection and thermal retention. Sulfuric acid clouds reflect sunlight back to space, while CO2 below retains absorbed energy. At altitudes of 50-70 kilometers, where pressures and temperatures are Earth-like, the upper atmosphere has strong winds and superrotation, transporting heat around the planet in about 4 Earth days. Venus's volcanism also plays a role in maintaining its greenhouse effect. Radar mapping from NASA's Magellan mission in 1994 revealed over 1,600 major volcanic structures, including shield volcanoes as large as 300 kilometers across. Volcanic activity releases CO2 and sulfur dioxide into the atmosphere, replenishing greenhouse gases and maintaining the high surface temperature. Some studies suggest that Venus may still be volcanically active today, meaning its atmospheric composition could be actively sustained rather than purely ancient. This extreme heating has profound implications for planetary science and climatology. Venus serves as a natural laboratory for understanding climate runaway scenarios. By comparing Venus's dense CO2-dominated atmosphere with Earth's 0.04% CO2, scientists can model how increasing greenhouse gases affect temperature, cloud formation, and energy balance. Understanding Venus also informs exoplanet research. Observations of hot super-Earths and sub-Neptunes show that thick atmospheres can decouple a planet's surface temperature from stellar distance, making proximity to the star only one factor in habitability. Distance from the Sun is not the sole determinant of temperature. Composition, pressure, cloud dynamics, and atmospheric circulation play a larger role. Mercury may be closer, but without an atmosphere to trap heat, it experiences more extreme temperature swings than Venus. Earth isn't perfectly round. We often picture Earth as a smooth, perfect blue marble floating in space. Maps, globes, and digital simulations reinforce this illusion of uniformity. In reality, Earth is far from perfectly spherical. Instead, it is an oblate spheroid, slightly flattened at the poles and bulging at the equator. This shape is primarily a result of Earth's rotation. As the planet spins at roughly 1,670 kilometers per hour, or 1,040 miles per hour at the equator, centrifugal force pushes mass outward. The equatorial diameter measures about 12,756 kilometers, or 7,926 miles, while the pole-to-pole diameter is roughly 12,713 kilometers, or 7,900 miles, a difference of 43 kilometers, or 27 miles. Though subtle on a planetary scale, this bulge has measurable effects on gravity, ocean circulation, and satellite navigation. Because of this equatorial bulge, objects at the equator are slightly farther from Earth's center than objects near the poles. Gravity decreases with distance from the center, so someone standing on the equator experiences slightly less gravitational pull than a person at the North Pole. The difference is small but measurable, roughly 0.5%, enough to make a person weighing 70 kilograms at the poles weigh about 350 grams less at the equator. Earth's uneven shape is compounded by variations in mass distribution. Mountains, ocean trenches, and dense rock formations all influence local gravity. For instance, the Himalayas and the Andes create slight gravitational anomalies, while deep trenches, like the Mariana Trench, slightly reduce gravity above them. To account for these irregularities, scientists use a model called the geoid, a mathematically defined surface that represents mean sea level across the globe, taking into account variations in gravity. Satellite missions have transformed our understanding of the geoid. The GRACE, or Gravity Recovery and Climate Experiment mission, launched in 2002, mapped Earth's gravitational field with unprecedented precision. Using twin satellites to measure minute changes in distance caused by gravitational anomalies, GRACE revealed fluctuations in mass distribution caused by ice sheet loss, groundwater depletion, and ocean circulation. Its successor, GRACEFO, continues to track these changes, helping scientists monitor climate shifts and tectonic activity. Earth's rotation also influences ocean behavior. The equatorial bulge contributes to the Coriolis effect, which causes moving air and water to curve rather than move in straight lines. This deflection shapes global wind patterns, drives the rotation of ocean gyres, and determines storm paths. Even our concept of altitude relies on understanding Earth's oblate shape. Mountains aren't measured simply by height above the center of the planet, but relative to the geoid. Mount Everest, the tallest mountain above sea level, at 8,848 meters or 29,029 feet, is actually farther from Earth's center than Chimborazo in Ecuador, which rises 6,263 meters or 20,548 feet above sea level. Because Chimborazo sits on the equatorial bulge, its peak is about 2,150 meters farther from Earth's center than Everest's summit. Earth's uneven distribution of mass also affects satellites in orbit. The bulge and gravitational variations cause small but cumulative perturbations in satellite trajectories, requiring careful adjustments to maintain precise orbits. GPS, weather satellites, and scientific spacecraft all rely on models that account for these subtleties. Without factoring in Earth's oblate shape and mass irregularities, positioning errors could accumulate, degrading the accuracy of systems that billions of people depend on daily. Historically, the misconception of a perfectly round Earth was convenient for astronomy, navigation, and mathematics. Ancient Greek thinkers like Eratosthenes, who calculated Earth's circumference in the 3rd century BCE, assumed a near-spherical planet, which was close enough for practical purposes. Even today, maps and globes simplify Earth's shape for readability. Tectonic movement, mantle convection, and seasonal mass redistribution from melting ice and ocean currents continually modify the planet's gravitational field and surface shape. Mars is not red everywhere. For generations, Mars has been nicknamed the Red Planet. From telescopic sketches in the 1800s to science fiction and Hollywood portrayals, it's always depicted as a dusty, crimson desert. Yet standing on its surface reveals a more nuanced reality. Mars is not uniformly red. Its colors are a mosaic shaped by chemistry, weather, and geology. The iconic reddish hue comes primarily from iron oxide, the same compound that gives rust its color. Billions of years ago, liquid water interacted with iron-rich minerals in the Martian crust, oxidizing them. As the water evaporated, fine dust coated the planet's surface, forming a thin, powdery layer of iron oxide. Sunlight scattering through this layer gives Mars its familiar red tint when observed from Earth. However, this red dust is only superficial. Beneath it, Mars's rocks display a spectrum of colors. NASA's Curiosity and Perseverance rovers have documented terrain that ranges from brown and tan to grey, with occasional greenish hues. Much of the crust is basaltic rock, formed from cooled volcanic lava, which appears dark or charcoal-coloured where dust is thin. Ancient cratered highlands reveal blue-grey tones, characteristic of unoxidized basalt, showing the planet's geochemical diversity. Global dust storms, a hallmark of Martian weather, can temporarily unify these colours. During massive storms such as the one in 2018 that silenced the Opportunity rover for months, iron oxide dust spreads worldwide, coating darker regions and giving the planet a uniform red appearance. Once the storm subsides, local winds reveal darker rocks again. Even the sky of Mars defies the red stereotype. The thin atmosphere, dominated by carbon dioxide, contains fine dust particles much smaller than grains of sand. During the day, these particles scatter sunlight through Mie scattering, producing a butterscotch or light orange sky. At sunset, the effect reverses. Blue light passes through more efficiently, casting a bluish-grey glow around the setting Sunday. Color variations also reveal the planet's geological history. Ancient regions like Oxyaplanum and Mare Thalis show clay minerals in green and bluish-grey tones, evidence of water-altered rocks. Hematite-rich plains near Meridiani Planum appear dark red, while volcanic regions such as the Tharsis Plateau remain darker and less oxidized. These spectral fingerprints allow scientists to map ancient riverbeds, lake deposits, and lava flows. Orbiters such as Mars Reconnaissance Orbiter, or MRO, and ESA's Mars Express have provided high-resolution mineralogical maps using infrared spectroscopy. These observations confirm that Mars is visually and chemically diverse. Polar regions add another twist. Frozen carbon dioxide ice appears bright white, while patches of water ice show subtle blue hues, a stark contrast to the red plains. Even seasonal sublimation of CO2 frost at the poles creates temporary dark streaks on the surface, dynamically altering the planet's appearance. Mars's color story is also influenced by dust composition and particle size. Smaller grains scatter light differently than larger particles, while local chemistry can alter the exact shade of red or brown. Observations from the Mars Color Imager, or MARCI, on MRO show regional differences in tone that correspond to geological age, wind patterns, and the presence of ancient water-altered deposits. The nickname Red Planet persists because it reflects the surface dust visible from Earth. Mars has layered terrain and a variety of surface colors, from dark basalt of volcanic plains to icy whites and blues of polar caps and green clay deposits. Surface and atmospheric interactions influence these color variations. Jupiter's Great Red Spot isn't permanent. Jupiter's Great Red Spot, or GRS, is one of astronomy's most iconic features, a massive storm larger than Earth itself, swirling with furious winds and vibrant colors. Yet despite its fame, it is neither eternal nor static. Historical observations, modern spacecraft data, and atmospheric modeling reveal that the GRS is a dynamic, evolving system that may not persist indefinitely. The earliest telescopic observations of Jupiter in the 1600s recorded large, oval features on its southern hemisphere. Astronomers such as Giovanni Cassini and Robert Hooke noted shapes that could correspond to storms, but their resolution was limited. It wasn't until the late 19th century that the Great Red Spot, as we recognize it today, was continuously tracked. The GRS is an anticyclonic storm, meaning it rotates counterclockwise in Jupiter's southern hemisphere. Winds within the storm reach 400 and 3,680 kilometers per hour, or 425 miles per hour, far exceeding the strongest terrestrial hurricanes. The storm exists between two powerful jet streams moving in opposite directions, creating a relatively stable zone that allows the vortex to persist. Yet high-resolution data from the Hubble Space Telescope and NASA's Juno spacecraft reveal that the storm is shrinking over time. In the 1800s, the GRS spanned roughly 40,000 kilometers across, wide enough to contain 3 Earths side by side. Today, it measures closer to 16,000 kilometers, only slightly larger than Earth itself. Its color has also faded from deep brick red to paler orange, indicating changes in the storm's composition and atmospheric chemistry. The reddish hue of the GRS likely originates from chromophores' complex organic molecules, formed when ultraviolet sunlight interacts with ammonia, acetylene, and other compounds in Jupiter's upper atmosphere. These molecules accumulate in the storm's clouds, tinting them red. Variations in solar activity, vertical atmospheric mixing, and chemical reactions within the clouds can cause fluctuations in color intensity over time. Juno's close flybys have provided unprecedented 3D mapping of the GRS, showing that the storm extends approximately 300 kilometers deep into Jupiter's atmosphere. While this may sound immense, it is shallow compared to Jupiter's massive radius of 71,492 kilometers. This relatively thin structure suggests that the GRS is more akin to a floating vortex than a deep, anchored system. surrounding jet streams generate turbulent shear along the edges, gradually eroding the storm and contributing to its observed shrinkage. Jupiter's atmosphere is a cauldron of turbulence, with smaller vortices forming frequently. Some last only a few months, while others merge with larger storms. These interactions suggest that massive storms like the GRS are part of a natural atmospheric cycle. Jupiter's internal heat flux energy, radiating from its core at about 1.7 times the solar energy it receives, powers convection, sustaining long-lived storm. Yet even with this constant energy input, the GRS is not immune to decay. Historical records hint that the storm has changed in size and shape over centuries. Observations in the late 19th and early 20th centuries describe an oval more elongated than today's nearly circular feature. Photographs from the Voyager missions in the 1970 seconds showed a similar large oval, while Hubble observations from the 1990 seconds onward documented steady contraction. By combining these historical records with modern data, scientists estimate that the storm's major axis has been shrinking at an average rate of 0.2% per year. Collisions with smaller storms occasionally rejuvenate the GRS temporarily. Juno observed baby storms merging with the Great Red Spot, injecting fresh energy and sustaining its intensity. Observations show that the storm continues to shrink gradually over time. The Great Red Spot's evolution also provides insight into planetary meteorology. Unlike Earth, Jupiter lacks a solid surface, allowing storms to persist for centuries because there is no frictional dissipation with land masses. Convection is fueled entirely by internal heat and differential rotation, producing longevity unmatched by terrestrial storms. Studying the GRS helps scientists analyze large-scale fluid dynamics relevant to gas giant atmospheres. Observations indicate that the GRS may continue to shrink and change in color over time. New atmospheric features may form nearby, while the storm gradually alters in size and intensity. Saturn's rings are younger than you think. For centuries, Saturn's rings were assumed to be ancient relics from the birth of the solar system, 4.5 billion years ago. Early astronomers, from Galileo to Huygens, marveled at their elegance, but lacked the tools to understand their composition or origin. Even in the 20th century, many textbooks presented the rings as primordial, a timeless feature accompanying Saturn since its formation. Data from NASA's Cassini mission later indicated that the rings are likely much younger, possibly no older than 100 million years. Cassini's gravity measurements, collected during its grand finale, dives between Saturn and its innermost rings in 2017, helped recalibrate our understanding. The spacecraft measured subtle perturbations in Saturn's gravitational field caused by the mass of the rings. These measurements indicated that the rings have much less mass than previously estimated, roughly 1/500th, the mass of Saturn, or the equivalent of a small icy moon like Mimas. The composition of the rings reinforces this idea. Spectroscopic analysis shows they are 95–98% water ice, with only trace amounts of silicate dust and rock. This explains their remarkable brightness. The ice reflects sunlight nearly as efficiently as freshly fallen snow on Earth. Cassini's visual and infrared mapping spectrometer, VIMS, found variations in particle size from micrometer-scale grains to boulders tens of meters across, all orbiting Saturn in an intricate, delicately balanced system governed by gravity and electromagnetic interactions with the planet's magnetosphere. One leading hypothesis involves the tidal disruption of an icy moon. Saturn's gravity is immense. Its Roche limit, the distance within which tidal forces can tear apart a body held together only by self-gravity, extends about 147,000 kilometers from the planet. If an icy moon ventured too close, Saturn's tidal forces could have shredded it, scattering debris into orbit. Over millions of years, collisions and gravitational resonances spread this material into the flat disk we observe today. Another possibility is catastrophic cometry, or asteroid collisions. Cassini detected evidence that impacts by comets or smaller moons could produce sufficient fragments to generate rings of significant mass. Models suggest that multiple smaller events, rather than a single catastrophic disruption, may have contributed to the current structure. This would explain the mixture of particle sizes and the presence of faint, diffuse ringlets, in addition to the bright main rings. Cassini also discovered that the rings are gradually losing material in a process called ring rain. Charged particles from the rings spiral along Saturn's magnetic field lines and eventually plunge into the planet's upper atmosphere, carrying water ice and other compounds. Measurements suggest that approximately 1,000 to 2,000 kilograms of material fall into Saturn every second. Models predict that the rings could disappear within 300 million years. The dynamic nature of the rings is also evident in their intricate structures. The main rings, A, B, and C, are interspersed with thousands of narrow ringlets, gaps, and waves caused by gravitational interactions with Saturn's moons. For instance, the Encke gap is maintained by the small moon Pan, which orbits within it, while spiral density waves throughout the rings trace the locations of resonances with larger moons like Mimas and Janus. Even subtle perturbations from Saturn's oblateness, the equatorial bulge caused by its rapid rotation, create oscillations and bending waves in the rings. Cassini's data revealed that these structures are constantly shifting, colliding, and reforming, proving that the rings are alive with motion and change. If the rings are less than 100 million years old, Saturn may have existed for most of its history without significant rings. The rings visible today may have formed from a cometary collision or tidal disruption, and similar processes could produce new rings in the future. Studying the rings helps scientists understand the physics of disk systems elsewhere in the universe. The interactions between ice particles, gravitational resonances, and electromagnetic forces resemble processes in protoplanetary disks around young stars, where planets form. Saturn's rings are a relatively young and dynamically evolving feature. Their structure and composition are shaped by disruptions and gravitational forces, and observations show that their size, brightness, and particle distribution change over time. Uranus isn't blue because of ice. Uranus is often described as a pale blue or turquoise planet, and many assume that its color comes from frozen water or icy methane on its surface. But this is a misconception. Uranus has no solid surface at all. It's a gas giant in the sense that it's mostly fluid, and its blue hue is not caused by ice in the conventional sense. Its color is a subtle optical effect produced by atmospheric chemistry and the way sunlight interacts with the planet's upper layers. The primary cause of Uranus's cyan tint is methane gas. Methane absorbs red light wavelengths and allows blue and green wavelengths to scatter back into space. Observations from the Hubble Space Telescope and ground-based data from the Keck Observatory show that Uranus's upper atmosphere contains a thin haze of methane ice crystals mixed with other hydrocarbons such as ethane and acetylene. This haze scatters sunlight, contributing to the planet's paler tone compared to Neptune. Uranus's atmosphere is composed primarily of hydrogen, about 83%, and helium, about 15%, with methane making up roughly 2% of the upper layers. Deeper in the planet, pressures and temperatures increase dramatically, reaching levels where water, ammonia, and methane exist as supercritical fluids, states of matter that are neither liquid nor gas. Despite being called an ice giant, these compounds are not frozen in the upper atmosphere. The term refers to the planet's internal composition, where these volatiles dominate the mass. Uranus's visible color has almost nothing to do with the presence of ice in the conventional sense. One factor that differentiates Uranus from Neptune is the thickness and altitude of its haze layers. Infrared and near-infrared spectroscopy from Hubble and Keck show that Uranus's methane haze extends roughly 5,100 kilometers above the main cloud deck, scattering sunlight before it can penetrate deeper layers. Neptune's haze is thinner and located deeper in the atmosphere, allowing more blue light to escape, which explains why Neptune appears richer and more saturated in color, even though its methane concentration is slightly higher than Uranus's, at about 2.5%. Uranus has an axial tilt of 98 degrees. Unlike other planets, which rotate more upright, Uranus rolls along its orbit, producing extreme seasonal variations. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness during its 84-year orbit. This tilt affects how sunlight interacts with the atmospheric haze, causing subtle changes in the reflected light that can make the planet appear slightly greener or grayer depending on viewing angle. The upper atmosphere of Uranus is about 49 K, or negative 224 degrees Celsius, the coldest planetary atmosphere in the solar system. This temperature allows methane ice crystals to persist in the haze layer, even though deeper layers remain fluid due to high pressure. The temperature inversion and weak internal heat limit convection in the atmosphere. Unlike Neptune, which emits roughly 2.6 times more heat than it receives from the Sun, Uranus radiates almost no excess heat. Cloud features on Uranus are faint and difficult to detect, but observations during equinox periods have revealed bands and occasional storms. In 2014, Hubble and Keck images captured bright storms near the northern hemisphere, with altitudes rising hundreds of kilometers above the cloud deck. These storms are composed primarily of methane ice clouds, but they do not dramatically alter the planet's overall hue. Instead, they appear as transient streaks against a soft cyan background. The blue color of Uranus results from methane absorption, haze scattering, seasonal effects due to axial tilt, and the planet's low internal heat. The observed cyan hue arises from interactions of sunlight with the upper atmosphere. Uranus is not icy in the way we experience ice on Earth. Its water, ammonia, and methane exist deep within a supercritical fluid interior, forming a layer hundreds of kilometers below the visible cloud tops. The term ice refers to volatile chemistry rather than frozen terrain. Uranus's cyan color results from atmospheric processes including methane absorption, haze scattering, and seasonal effects caused by axial tilt. Its visual appearance reflects the physics of sunlight interacting with the upper atmosphere of a planet with a largely fluid interior. Neptune moves faster than expected. Neptune, the most distant of the known major planets in our solar system, receives less than 0.1% of the Sun's energy compared to Earth, yet hosts the fastest winds recorded anywhere in the solar system. These winds can reach 2,100 kilometers per hour or 1,300 miles per hour, exceeding the speed of sound at sea level on Earth. The answer lies deep within Neptune itself. Unlike Earth, whose climate is driven primarily by sunlight, Neptune's storms are fueled by internal heat, left over from its formation 4.5 billion years ago. Observations show that Neptune radiates roughly 2.6 times more energy than it absorbs from the Sun, releasing heat stored in its interior in a slow, convective process. Warm gases rise from the planet's inner layers, while cooler gases sink, generating turbulence that powers the planet's supersonic winds. Scientists estimate that this internal heat flux is around 0.433 watts per square meter, enough to sustain some of the largest storms ever recorded. Neptune's atmosphere plays a crucial role in shaping its ferocious winds. It is composed primarily of hydrogen 80%, helium 19%, and methane 1 to 2%. Methane absorbs red light, giving Neptune its characteristic deep blue color, but it also traps heat, contributing to vertical temperature differences. Temperature contrasts between the upper atmosphere, which hovers around -218 degrees Celsius or -360 degrees Fahrenheit, and deeper layers, which can reach -200 degrees Celsius or -328 degrees Fahrenheit, drive vertical convection currents. These currents act like atmospheric elevators, accelerating gases and amplifying horizontal wind speeds. Unlike Jupiter's familiar Great Red Spot, Neptune's most iconic storm is the Great Dark Spot, first observed by NASA's Voyager 2 spacecraft during its historic 1989 flyby. This storm, roughly the size of Earth at 13,000 kilometers across, was a high-pressure anticyclonic system with winds exceeding 2,400 kilometers per hour or 1,500 miles per hour in localized areas. Yet, in stark contrast to Jupiter's centuries-old vortex, Neptune's dark spots are ephemeral. The original Great Dark Spot vanished within a few years, replaced by new, transient storms detected by the Hubble Space Telescope. These observations reveal a planetary atmosphere that is surprisingly dynamic and continually evolving. Even far from the Sunday, Neptune's wind patterns are more complex than a simple equatorial rotation. Winds flow in alternating bands, with some moving eastward and others westward. These zonal jets form from differences in atmospheric density, pressure gradients, and rotation-induced Coriolis effects. The planet's lack of a solid surface means minimal friction, allowing winds to accelerate to extreme speeds. In some regions, the wind shear between bands can exceed 500 kilometers per hour, producing turbulence that fragments and reshapes storms over time. Gravity and magnetic fields also influence Neptune's atmospheric behavior. Unlike the nearly symmetrical fields of Earth or Jupiter, Neptune's magnetic field is tilted by 47 degrees relative to its rotation axis and offset by roughly 0.55 planetary radii from the center. This unusual configuration interacts with charged particles from the solar wind, possibly altering upper atmosphere circulation and energizing the auroras that dance over the poles. Neptune's auroras, while far dimmer than Jupiter's, are still visible in ultraviolet wavelengths and hint at the planet's complex electromagnetic environment. The planet's rotation contributes further to its atmospheric intensity. Neptune completes a rotation in just 16 hours, creating strong Coriolis forces that bend wind paths into zonal flows and large vortices. The combination of rapid rotation, internal heating, and atmospheric stratification generates storms that can grow to scales comparable to Earth itself. For example, the Scooter, a smaller white cloud feature observed by Voyager 2, moved at 2,100 kilometers per hour, demonstrating that not only the largest storms, but even mid-sized systems experience extraordinary velocities. Even Neptune's orbit has caused intrigue. Early 19th and 20th century astronomers noticed subtle perturbations in Uranus's path, which led to the prediction and eventual discovery of Neptune in 1846. Later, similar orbital irregularities in Neptune's trajectory inspired the concept of a hypothetical Planet X, a planet beyond Neptune influencing its orbit. While refined measurements and better understanding of gravitational interactions resolved most anomalies, these historical episodes underscore how Neptune's mass and gravity reach far beyond its visible sphere. Neptune's internal structure is key to sustaining its powerful atmosphere. Gravity data from Voyager 2 and models of planetary composition suggest that Neptune has a rocky core of 1.5 Earth masses, surrounded by a dense mantle of water, ammonia, and methane ices. Above this lies the thick hydrogen-helium envelope, extending thousands of kilometers. The core generates heat through slow radioactive decay and residual gravitational contraction, while the mantle's fluid ices enable efficient heat transport to the atmosphere. This structure explains how a planet so distant from the Sun can sustain supersonic winds and massive storm systems. Observations in the past 2 decades have highlighted additional surprises. Neptune exhibits small-scale transient cloud systems, particularly along its southern mid-latitudes. The Hubble Space Telescope documented dozens of these clouds, moving at speeds exceeding 2,000 kilometers per hour, forming, merging, and dissipating within weeks. These short-lived storms suggest a continuous recycling of energy within the atmosphere, a process that could theoretically persist for billions of years if internal heat continues to escape. Neptune's winds demonstrate how internal heat can dominate planetary weather systems, independent of solar energy. Observations of hot Neptunes, orbiting close to their stars, show similar high-velocity winds and dynamic weather, suggesting comparable atmospheric mechanisms across planets with similar mass or composition. Neptune's winds, storms, and atmospheric activity result from internal heat, rapid rotation, and magnetic influences. These factors sustain extreme motion despite the planet's distance from the Sun. Neptune remains active, with persistent winds and storms that illustrate the effects of internal heat and atmospheric dynamics at the edge of the solar system. The Moon is not dead. For generations, the Moon was seen as a geological ghost, a silent relic of the solar system's past, frozen in time since its violent birth 5 billion years ago. Textbooks and documentaries portrayed it as a dead world, lacking atmosphere, magnetic field, or any hint of internal life. Yet over the past few decades, a different picture has emerged. The Moon is not as inert as we once believed. Beneath its pale surface lies evidence of residual heat, internal stress, and even seismic activity signs of a world still subtly alive. The first real clues came from the Apollo missions. Between 1969 and 1972, astronauts from Apollo 11, 12, 14, 15, and 16 placed a network of seismometers across the lunar surface. Over the next 8 years, these instruments recorded more than 12,000 moonquakes, revealing a surprising range of activity. There were 4 main types: shallow moonquakes, deep moonquakes, thermal quakes caused by sunrise heating, and vibrations from meteorite impacts. The deep moonquakes, occurring 700 to 1,200 kilometers below the surface, were especially intriguing. They repeated in cycles tied to the Earth-Moon tidal relationship, a clue that gravitational flexing was still stirring the Moon's interior. The strongest moonquakes registered magnitudes between 4 and 5 on the Richter scale, enough to rattle the lunar crust for tens of minutes. Because the Moon lacks water or atmosphere to damp vibrations, its surface rings for a long time after a quake, much like a struck bell. This sustained reverberation implies the lunar crust is brittle and rigid, but not entirely motionless. Half a century later, modern missions revisited the data with new tools. In 2019, a study led by Thomas Waters of the Smithsonian Institution reanalyzed Apollo seismic data using modern algorithms and high-resolution imagery from the Lunar Reconnaissance Orbiter, or LRO. The team found that many shallow moonquakes, those occurring 20 to 30 kilometers below the surface, clustered near geologically young fault scarps. These scarps are small, cliff-like formations where the crust has broken and thrust upward, some stretching for tens of kilometers and rising tens of meters high. Their sharp edges and lack of erosion suggest they formed recently, perhaps within the last 50 million years, a blink of an eye in lunar time. These scarps formed as the Moon slowly cooled and contracted, shrinking by roughly 150 feet or 50 meters over the past several 100 million years. As the interior loses heat, it compresses, forcing the outer crust to wrinkle and break. This process is ongoing, meaning that the Moon is still cooling and still adjusting its shape. The GRAIL, or Gravity Recovery and Interior Laboratory mission, launched in 2011, deepened this story. By precisely mapping the Moon's gravitational field, Grail uncovered vast mass concentrations, mascons, buried beneath ancient impact basins such as Imbrium, Serenitatis, and Crisium. These mascons are denser regions in the crust, likely caused by magma upwellings that solidified after colossal impacts. The variations in gravitational strength across the lunar surface suggest that the Moon's mantle remains somewhat ductile and that slow internal movement may still be occurring. Another revelation came from thermal modelling. Although surface temperatures swing wildly between 127 degrees Celsius or 260 degrees Fahrenheit in daylight and 173 degrees Celsius or 280 degrees Fahrenheit at night, deeper regions stay much warmer. Models indicate that mantle temperatures could still exceed 1,200 degrees Celsius or 2,200 degrees Fahrenheit in isolated pockets. This residual heat comes partly from the decay of radioactive isotopes uranium-238, thorium-232, and potassium-40 left over from the Moon's formation. These isotopes act like embers in a dying fire, providing just enough warmth to drive occasional geological adjustments and possibly explain the remaining seismic activity. Volcanism, too, hasn't been entirely absent in recent lunar history. The Mare basalt's vast, dark plains visible from Earth are remnants of lava flows that flooded the Moon's lowlands billions of years ago. For decades, scientists assumed the last of these flows solidified more than 1 billion years ago. However, images from LRO and Japan's Selene Kaguya orbiter challenge that view. Regions such as Ina Crater, Sosigenes, and Marius Hills show unusually fresh volcanic features, their surfaces lightly cratered and sharply defined. Crater count dating suggests some of these flows could be as young as 5,100 million years old, meaning small volcanic eruptions might have occurred during the age of dinosaurs on Earth. If true, that would mean the Moon's mantle retained molten pockets far longer than once believed. Some models propose that small-scale volcanic outgassing, particularly of carbon monoxide, water vapor, and sulfur, may still occur occasionally through microscopic fissures. Instruments on the Lunar Atmosphere and Dust Environment Explorer, or LADE, detected transient increases in helium and argon, possibly linked to recent outgassing or impacts. The Moon's magnetic story adds another dimension. While it lacks a global magnetic field today, lunar rocks collected by Apollo astronauts contain traces of ancient magnetism. Measurements indicate that around 3.5 to 4 billion years ago, the Moon had a magnetic field as strong as Earth's current one, about 50 microteslas. That field likely came from a dynamo effect in a molten, convecting metallic core. Over time, as the Moon cooled, the dynamo faded. Yet, local magnetic anomalies persist, especially near Rhina Gamma and other swirl-like regions, where crustal magnetization may protect the surface from solar wind erosion. These magnetic remnants are faint whispers of a once lively magnetic engine deep within the Moon. Even the surface itself is far from static. Constant bombardment by micrometeorites pulverizes the top layer into fine dust, forming the regolith, which can be several meters thick. Solar wind particles embed hydrogen and helium into the dust grains, subtly altering their chemistry. Around the terminator, the boundary between lunar day and night, electrical charging of dust causes it to levitate temporarily. The Surveyor landers in the 1,960 seconds, and later, the Apollo 17 astronauts reported a mysterious horizon glow, possibly caused by this levitating dust-scattering sunlight. Such processes show that the Moon's surface environment is still active, even if its movements are microscopic. Future missions will test these discoveries directly. NASA's Artemis program, which aims to return humans to the Moon later this decade, plans to install modern seismometers, heat probes, and magnetometers. The proposed Lunar Geophysical Network could create a permanent system of instruments spread across the surface, allowing scientists to map moonquake sources and measure ongoing crustal contraction. European and Chinese lunar missions are also expected to carry complementary sensors, giving researchers a 360-degree view of lunar interior dynamics. Europa's ocean is bigger than Earth's. When Galileo Galilei first turned his telescope toward Jupiter in 1610, he discovered 4 bright moons circling the giant planet, a revelation that reshaped astronomy. One of those moons, Europa, appeared as a small, smooth disk, unremarkable compared to Jupiter's colourful storms. For centuries, it was assumed to be little more than a frozen rock. Today, Europa stands as one of the most intriguing worlds in the solar system, a place that may hold an ocean larger than all of Earth's combined seas, and possibly the ingredients for life itself. Europa's surface is one of the smoothest in the solar system. Instead of being heavily cratered like the Moon or Mercury, it's covered with bright ice streaked by long, intersecting cracks and ridges. These markings, some stretching thousands of kilometers, trace a restless crust that shifts and fractures under the pull of Jupiter's immense gravity. The lack of impact craters tells a clear story. Europa's surface is geologically young, constantly renewed by forces rising from within. At first glance, Europa looks like a solid block of ice, but spacecraft data reveal that this is only the outer shell. Beneath the frozen crust lies a global saltwater ocean, sealed beneath 15 to 25 kilometers of ice. This ocean may reach depths of 60 to 150 kilometers, making it 10 times deeper than Earth's average ocean. With Europa's diameter just 3,121 kilometers, about 90% that of our Moon, this subsurface sea could hold 2 to 3 times more liquid water than all of Earth's oceans combined. The question is, what keeps all that water liquid in the frigid outer solar system, where sunlight is 25 times weaker than on Earth? The answer lies in a process known as tidal heating. As Europa orbits Jupiter every 3.55 Earth days, its slightly elliptical path causes constant stretching and squeezing of its interior due to Jupiter's gravity. This flexing generates heat through friction, much like how bending a metal wire back and forth makes it warm. The heat produced inside Europa prevents its ocean from freezing solid, even though surface temperatures drop to 160 degrees Celsius or 260 degrees Fahrenheit. This internal heating is strong enough to maintain geological activity beneath the ice. Data from the Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided the first strong evidence of this hidden ocean. The spacecraft detected fluctuations in Europa's magnetic field, which scientists interpreted as being induced by an electrically conductive layer, most likely a salty global ocean. Galileo also photographed long cracks filled with fresh, bright ice, suggesting that material from the subsurface was rising to the surface and freezing. Additional support came from the Hubble Space Telescope, which in 2012 and again in 2016 observed water vapor plumes erupting hundreds of kilometers above Europa's surface. These plumes appear to emerge from regions near the South Pole and may be caused by pressure from the ocean below, forcing water through cracks in the ice. If confirmed, these plumes are a scientific treasure. They could allow spacecraft to directly sample Europa's ocean materials without the need to drill through kilometers of ice. The potential size of Europa's ocean is staggering. Earth's total ocean volume is about 1.332 billion cubic kilometers, while Europa's may exceed 3 billion cubic kilometers. But beyond size, the ocean's environment might be surprisingly Earth-like, at least in its chemistry. Scientists believe the ocean is salty, with concentrations of magnesium sulfate and sodium chloride similar to seawater. It likely interacts with the Moon's rocky mantle, creating conditions for hydrothermal vents on the ocean floor, environments on Earth known to teem with microbial life. In 2009, a team using the Keck Observatory in Hawaii detected sodium chloride or table salt on Europa's surface. This discovery hinted that the subsurface ocean interacts with a rocky seabed just as Earth's oceans do. Meanwhile, infrared spectral data from NASA's Galileo and later from Hubble revealed the presence of compounds such as sulfur dioxide, carbonates, and possibly organic molecules, all chemical ingredients that could support metabolic reactions if life exists there. Europa's constant gravitational stretching doesn't just produce heat, it reshapes the surface itself. Vast regions known as chaos terrains show shattered blocks of ice that appear to have floated, rotated, and refrozen. These chaotic patterns are likely caused by localized melting and refreezing near the surface, possibly where pockets of water or slushy ice rise from the ocean below. This dynamic resurfacing suggests Europa's crust and ocean are actively interacting, possibly exchanging materials, a key condition for maintaining chemical energy gradients that could support life. Upcoming missions are set to transform our understanding of this enigmatic world. NASA's Europa Clipper, scheduled to launch in 2026, will conduct nearly 50 flybys of the Moon, coming as close as 25 kilometers above the surface. It will carry a suite of advanced instruments, including an ice-penetrating radar, a mass spectrometer, and a thermal imaging camera designed to study the thickness of the ice shell, map surface chemistry, and analyze the composition of plumes if they're active during flybys. Meanwhile, the European Space Agency's JUICE mission, or Jupiter Icy Moons Explorer, launched in 2023, will explore Europa along with Ganymede and Callisto. JUICE's instruments will study how Jupiter's magnetic field interacts with Europa's induced magnetic layer, giving indirect confirmation of the ocean's depth and salinity. Together, these missions will build a detailed picture of Europa's internal structure and its potential habitability. If hydrothermal vents do exist at Europa's seafloor, they could be strikingly similar to those found along Earth's mid-ocean ridges, where mineral-rich water meets chemical energy sources like hydrogen sulfide. On Earth, these vents host complex ecosystems, from bacteria and archaea to tube worms and crustaceans, all thriving without sunlight. If life could evolve under such conditions here, scientists argue, there's every reason to think it might exist on Europa as well, perhaps as microbial colonies clinging to mineral outcrops near underwater vents. Even the energy balance on Europa is intriguing. Its ocean is shielded from Jupiter's intense radiation by thick ice, but cracks and thin spots might occasionally allow surface oxidants to mix with the subsurface. These oxidants, created when radiation breaks apart surface molecules, could trickle down through fissures and feed chemical cycles below, providing a possible energy source for metabolism. Europa is now a major focus of astrobiological research. According to NASA scientist Robert Pappalardo, who leads the Europa Clipper mission, it is considered one of the most likely locations in the solar system where evidence of life could be found. Titan isn't just smog and methane. When early telescopes observed Saturn's largest moon, Titan appeared as a featureless orange sphere, obscured by thick haze. For decades, astronomers believed it was enveloped entirely in methane and hydrocarbon smog. Modern spacecraft observations later revealed that beneath this dense atmosphere lies a varied landscape shaped by liquid hydrocarbons and active weather systems. Discovered in 1655 by the Dutch astronomer Christiaan Huygens, Titan is larger than Mercury, with a diameter of 5,150 kilometers or 3,200 miles. It's the only moon known to possess a thick atmosphere, one so dense that surface pressure is 1.5 times Earth's. This atmosphere is primarily nitrogen, about 95%, with the remaining 5% composed mostly of methane, along with trace amounts of ethane, hydrogen, and complex organic molecules. Despite its alien chemistry, Titan's nitrogen-rich air makes it surprisingly similar, at least in structure, to Earth's. Titan's haze begins high above the surface, where ultraviolet sunlight and charged particles from Saturn's magnetosphere bombard methane molecules, breaking them apart. The fragments recombine into more complex hydrocarbons and nitriles, which clump into microscopic particles called Tholin's reddish organic compounds that give Titan its distinctive orange-brown hue. Over time, these particles drift downward, forming thick layers of organic snow that accumulate across the surface. For centuries, no one knew what lay beneath that haze. Then came NASA's Cassini-Huygens mission, a joint project with the European Space Agency and the Italian Space Agency. Cassini orbited Saturn for 13 years, from 2004 to 2017, while the Huygens probe detached and descended through Titan's atmosphere on the 14th of January 2005. What Huygens found astonished scientists. It photographed a world that looked eerily familiar, with rounded pebbles, river channels, and flat floodplains, all shaped by flowing liquids. But these rivers and lakes aren't filled with water. On Titan, where surface temperatures average 179 degrees Celsius or 290 degrees Fahrenheit, water behaves like rock, forming the bedrock and mountains. The liquids that shape the landscape are methane and ethane, hydrocarbons that are gases on Earth but remain liquid in Titan's frigid conditions. Cassini's radar mapping later revealed vast networks of rivers, deltas, and seas, particularly near the North Pole. Among these seas is Kraken Mare, the largest body of liquid on Titan, spanning an area of over 400,000 square kilometers, or 155,000 square miles bigger than all 5 of North America's Great Lakes combined. Other major seas, such as Ligeia Mare and Punga Mare, add to Titan's hydrocarbon abundance. Cassini data showed that some of these seas are hundreds of meters deep, with liquid compositions varying by region. Ligeia Mare, for instance, contains mostly methane, while Kraken Mare holds a mix of methane and ethane. These surface liquids form part of a complete methane cycle, mirroring Earth's water cycle. Methane evaporates from the seas, forms clouds in Titan's thick atmosphere, condenses into rain, and flows back across the surface through river channels. Cassini's near-infrared instruments even observed seasonal rainfall events, with dark patches appearing after storms and fading as the methane evaporated. Titan experiences seasons similar to Earth's, each lasting about 7 Earth years, due to Saturn's 29.5-year orbit around the Sun and its axial tilt of 26.7 degrees. Yet, Titan's wonders don't end at the surface. Gravity data from Cassini revealed that beneath its icy crust lies a subsurface ocean, likely composed of water mixed with ammonia, a chemical antifreeze that keeps the liquid from freezing solid. This ocean could be 50 to 100 kilometers deep, locked beneath an ice shell that may vary in thickness depending on geological activity. Some regions show signs of cryovolcanism, where icy magma, slushy water, and ammonia may have erupted through the crust in the distant past, resurfacing parts of the Moon. This buried ocean introduces the tantalizing possibility of habitability. While the surface is far too cold for life as we know it, the subsurface ocean could provide the liquid water and chemical energy necessary for microbial ecosystems. On Earth, life thrives in dark, extreme environments, such as deep-sea hydrothermal vents and subglacial lakes. Titan's interior, warmed by tidal flexing from Saturn's gravity and insulated by its thick crust, might offer similar conditions. Chemically, Titan is a treasure trove for astrobiologists. Its atmosphere is a natural laboratory for prebiotic chemistry, the formation of complex organic molecules before the emergence of life. The tholins that fall to the surface contain carbon, hydrogen, nitrogen, and oxygen, all essential elements for amino acids and nucleotides. Laboratory simulations on Earth have shown that when Titangent-like atmospheric gases are exposed to UV radiation or electric discharges, they produce a variety of organic compounds, some resembling the building blocks of life. The connection to early Earth is hard to ignore. Our planet's atmosphere, billions of years ago, may have resembled Titan's, rich in methane and nitrogen, before oxygen became abundant. By studying Titan, scientists can glimpse what Earth might have looked like before life transformed it, a frozen mirror of our own origins. One of the most exciting upcoming explorations of Titan is NASA's Dragonfly mission, scheduled to launch in 2028, arriving in the mid-2030s. Unlike traditional rovers, Dragonfly will be a nuclear-powered rotorcraft capable of flying between multiple sites across Titan's equatorial dunes. It will analyze surface material, measure atmospheric chemistry, and search for complex organic molecules. Its landing site, Shangri-La, lies near an impact crater called Selk, where past impacts may have melted ice and created temporary liquid water environments, ideal conditions for prebiotic chemistry. Titan's meteorology adds yet another layer of intrigue. Winds sculpt massive dunes near the equator, each stretching hundreds of kilometers, made not of sand, but of frozen organic grains. Methane storms sweep across the poles during seasonal changes, while fogs and clouds drift through the hazy sky. Cassini's instruments detected lightning-like radio emissions, hinting that even Titan's weather can be electrified, possibly triggering chemical reactions in its atmosphere. Titan exhibits many of the same physical processes observed on Earth, including erosion, rainfall, and atmospheric circulation. These processes operate with different materials and under colder conditions, producing methane-based weather and surface activity instead of water-driven systems. Titan's surface environment is characterized by an orange haze, low gravity, and cold plains of solid ice, bordered by liquid methane and ethane. The combination of dense atmosphere and active hydrocarbon cycles makes it a site of continued scientific interest for understanding planetary weather, chemistry, and surface processes. Pluto's heart isn't just a cute feature. When NASA's New Horizons spacecraft flew past Pluto on the 14th of July 2015, it captured detailed images that revealed Pluto's surface for the first time. The data showed a complex landscape shaped by ice and internal heat. At the center of this terrain lies a large, bright, heart-shaped region that quickly became the focus of scientific study. This feature, officially named Tombaugh Regio, after Pluto's discoverer Clyde Tombaugh, spans roughly 1,600 kilometers across about a quarter of the planet's diameter. It's not just a photogenic mark, it's the most geologically important area on Pluto's surface. Tombaugh Regio is made up of two distinct halves: the western lobe, called Sputnik Planitia, and the eastern lobe, a rugged, elevated region covered in older ice and highlands. Together, they reveal a world that is still surprisingly active. Sputnik Planitia is a vast plain composed of frozen nitrogen, carbon monoxide, and methane. Even though Pluto's surface temperature averages around 235 degrees Celsius, this frozen sheet is not completely still. Data from New Horizons showed enormous polygonal patterns, each cell 30 to 50 kilometers wide, formed by slow convection within the nitrogen ice. Warmer ice from deeper layers rises, cools near the surface, and sinks again. These cycles renew the surface over millions of years, keeping it almost entirely free of impact craters. The heat driving this motion likely comes from radioactive decay in Pluto's rocky core. Elements such as uranium, thorium, and potassium-40 release small amounts of heat as they break down. Over time, this trapped energy warms Pluto's interior just enough to soften the ice above. The ice acts as a sluggish fluid, capable of flowing and churning even under extreme cold. Sputnik Planitia sits inside an enormous impact basin, likely formed billions of years ago when a massive object struck Pluto. The depression left behind filled with volatile ices that condensed from Pluto's thin atmosphere. What's more, the basin's position almost exactly opposite Pluto's largest moon, Charon, isn't random. The extra weight of the dense nitrogen ice appears to have caused Pluto's outer shell to slowly reorient itself through a process known as true polar wander, moving the basin toward the equator where it could stabilize. This reshaping would have changed Pluto's balance, like a spinning top adjusting as one side becomes heavier. Below the surface, evidence points to a subsurface ocean of liquid water. Observations of fractures, ridges, and other surface deformations suggest internal expansion rather than contraction, implying that water once frozen melted and pushed outward. Models show that a layer of liquid water may exist 100 to 150 kilometers beneath the surface, kept from freezing solid by residual heat and antifreeze compounds like ammonia. Some estimates put the ocean's depth at tens of kilometers, rivaling or even surpassing Earth's deepest seas. The edges of Sputnik Planitia are bordered by mountain ranges made of water ice that behave like bedrock at these low temperatures. Some peaks rise 3 to 4 kilometers high. Nitrogen glaciers slowly flow outward from the basin, creeping around the mountains and refreezing as they cool. The movement of these glaciers closely resembles those on Earth, though here the ice is nitrogen rather than water. Pluto's thin atmosphere also interacts with this icy basin. Composed mostly of nitrogen with traces of methane and carbon monoxide, it's less than 1/100,000th the pressure of Earth's. But it is dynamic. As Pluto travels along its elongated 248-year orbit, the planet's surface and atmosphere exchange materials in a slow cycle. When Pluto nears the Sun, solar heat causes nitrogen to sublimate from the heart-shaped plane, thickening the atmosphere. When it moves away, the gases freeze back onto the surface, effectively making Sputnik Planitia act as a global nitrogen reservoir that breathes in rhythm with Pluto's orbit. Despite being nearly 6 billion kilometers from the Sun, Pluto's surface shows signs of recent activity. Crater counts reveal that parts of Sputnik Planitia are less than 10 million years old, remarkably young for such a small, cold world. Elsewhere, in regions like Wright Mons and Piccard Mons, dome-shaped structures hint at cryovolcanism, volcanic activity driven by water or ammonia instead of molten rock. These features, some over 150 kilometers wide, may have formed from eruptions that pushed icy material onto the surface only a few 100 million years ago. Color variations across Pluto also reveal chemical diversity. The bright white heart contrasts sharply with the dark reddish region known as Cthulhu Macula, which stretches along Pluto's equator. The red hue comes from Tholin's complex organic molecules formed when ultraviolet sunlight and cosmic rays break down methane in the atmosphere. These tholins slowly settle onto the surface, painting the dwarf planet with shades of gold, brown, and crimson. Tumor Regio's brightness and shape are not coincidences. The heart reflects more sunlight than any other part of Pluto, cooling it relative to its surroundings and reinforcing its ability to trap volatile ices. The region's boundaries mark the interface between old and new terrain, between stability and motion. It's an active system that connects the surface, the atmosphere, and possibly even the ocean beneath. Pluto shows ongoing geological and atmospheric activity, including nitrogen ice convection, glacial motion, and possible cryovolcanism. The region known as Sputnik Planitia illustrates how internal heat, surface processes, and volatile cycles interact even in distant, low-temperature environments. These findings indicate that Pluto remains an active world, rather than a static remnant of the early solar system. Asteroids are not just rocks. For much of the 20th century, asteroids were largely dismissed as cosmic afterthoughts, inert rocks drifting silently between Mars and Jupiter. That perception is now obsolete. Modern observations and spacecraft missions have revealed that asteroids are complex, evolving worlds, each with distinct histories, structures, and even potential clues to life's origins. They are far from simple rubble. They are miniature laboratories of planetary science. Asteroids vary widely in size, shape, composition, and internal structure. Some, like Ceres, measure nearly 950 kilometers across, while others are barely 10 meters wide. They are classified primarily by composition. C-type or carbon-rich asteroids comprise roughly 75% of known objects and contain water-bearing minerals and organics. S-type or silicaceous asteroids are made of silicate rocks and metals, and M-type or metallic asteroids consist mostly of nickel and iron, possibly remnants of cores from larger, disrupted protoplanets. Beyond these main categories, astronomers have identified rarer types such as V-type, made largely of basalt, and D-type, dark and primitive, resembling the composition of cometary nuclei. Early robotic encounters shattered the image of asteroids as inert boulders. The Near-Shoemaker mission, which orbited and landed on 33 Eros in 2001, revealed a rugged surface covered with regolith, fractures, and boulders, as well as grooves and ridges, indicative of stress from tidal forces and past collisions. Later missions expanded this understanding dramatically. Japan's Hayabusa mission returned the first samples from 25143 Itokawa in 2010, confirming that asteroids can be rubble piles, loosely bound aggregations of rock and dust rather than solid monoliths. Hayabusa 2 followed up in 2020 by retrieving material from 162173 Ryugu, showing hydrated minerals and organic compounds. These findings suggested that asteroids may have once contained water and could even have delivered it, along with prebiotic molecules, to the early Earth. The presence of water and organics is not just an academic curiosity. Infrared spectroscopy and sample analysis reveal that carbonaceous asteroids can contain up to 20% water by mass in hydrated minerals, a remarkable figure for objects long thought to be dry. Organic compounds, including amino acid precursors, have been detected, hinting that these small bodies may have played a role in seeding life on Earth. For example, Ryugu samples contained complex carbon compounds that resemble the building blocks of life. Bennu, visited by NASA's OSIRIS-REx in 2020, has a surface rich in hydrated clays, confirming that water chemically altered its rocks billions of years ago. Asteroids are not static either. Many are rotating rapidly, and sunlight can subtly change that rotation over time through the Yorp or Yarkovsky-O'Keefe-Radzievsky-Paddock effect. Uneven absorption and re-emission of sunlight produces tiny torques that can spin an asteroid faster, causing surface material to migrate toward the equator or even break free entirely. This explains why some asteroids, such as 66391 Moshub, possess small moons or elongated shapes. The DART mission in 2022 intentionally impacted Dimorphos, a moon of 65803 Didymos, demonstrating that these small bodies' spin and mass distribution can be altered, a key insight for planetary defense strategies. Many asteroids are surprisingly geologically diverse. Bennu, for instance, revealed boulders ranging from centimeters to tens of meters, creating a surface that's far from uniform. Radar observations of 21 Lutetia showed steep cliffs, ridges, and massive craters, suggesting a violent history of impacts and fragmentation. Vesta, visited by NASA's Dawn spacecraft, exhibits a differentiated interior, a dense metallic core, silicate mantle, and basaltic crust, indicating that it underwent heating and partial melting in the early solar system. These findings blur the line between asteroid and minor planet, highlighting their dynamic geological past. Magnetic fields are another surprise. Some M-type asteroids, like 16 Psyche, may retain weak remnant magnetism from a primordial dynamo or from being fragments of larger, differentiated bodies. This magnetic signature could provide insight into the early conditions of the solar system, including processes that formed planetary cores. Psyche itself, slated for exploration by NASA in 2026, may also harbour clues about how iron-rich bodies coalesced during planetary formation. Asteroids also interact actively with the space environment. Micrometeorite impacts, solar wind sputtering, and cosmic ray bombardment continuously modify surfaces, producing a layer of space-weathered material called regolith. Fine dust grains can be electrostatically charged and lofted, producing transient dust ponds observed on Eros and Itokawa. These processes are subtle yet ongoing, indicating that even small bodies are dynamic and evolving. From a practical perspective, asteroids are valuable beyond science. Near-Earth objects like Bennu and Ryugu are rich in metals such as nickel, iron, and platinum group elements, making them prime candidates for future resource utilization. Estimates suggest that a 500-meter metallic asteroid could contain metals worth tens of trillions of dollars at Earth market prices. Understanding asteroid composition and structure is crucial not only for scientific study, but also for potential mining, planetary defense, and deep space exploration. Asteroids provide a record of solar system evolution, preserve chemical and geological information about the formation of planets, and may have contributed water and organic compounds to the early Earth. Their structures and compositions illustrate the complexity and diversity of small bodies in the solar system. Comets aren't dirty snowballs. For centuries, comets were romanticized as blazing tails of fire streaking across the sky, and during much of the 20th century, astronomers described them simply as dirty snowballs, icy chunks of frozen water and dust loosely bound together. The concept, formalized by Fred Whipple in the 1950 seconds, suggested that comets were passive remnants of the solar system, largely inert and unchanging until they neared the Sunday. Modern space missions, however, have completely overturned that notion, revealing comets as chemically rich, physically complex, and remarkably active worlds. The ESA Rosetta mission to 67P, Churyumov-Gerasimenko, provided a detailed, unprecedented view of a comet's nucleus. When Rosetta arrived in 2014, it found a 4.1-kilometer long body shaped like a rubber duck, covered in cliffs, boulders, and pits. Its surface reflected only about 6% of incoming sunlight, darker than most coal, indicating a crust dominated by complex organic molecules. Beneath this dusty veneer lay water ice, carbon dioxide, carbon monoxide, and other volatiles, which sublimated through fractures to form the dramatic jets that defined cometary activity. The comet's nucleus is far from dense. Rosetta's measurements gave 67P a bulk density of just 0.53 grams per cubic centimeter, roughly half that of water. Such low density implies a highly porous interior, with voids and loosely packed layers that preserve clues about the solar system's formative condition. Scientists estimate its porosity at 70–75%, meaning much of its volume is empty space. This structure records billions of years of cosmic history, making 67P effectively a frozen time capsule. Rosetta's lander, Philae, drilled into the surface and revealed an astonishing chemical complexity. Organic molecules such as glycine, an amino acid, methyl isocyanate, and phosphorus compounds were detected, essential components for prebiotic chemistry. These findings suggest that comets could have delivered a significant fraction of Earth's organic inventory during the late heavy bombardment roughly 4 billion years ago. Similar compounds have also been found in carbonaceous meteorites, pointing to a shared chemical heritage within the solar system. The comet's activity is not uniform or predictable. Sublimation-driven jets erupt from specific regions, some linked to the neck area between the comet's two lobes, while other vents open and close depending on sunlight angle and seasonal heating. Surface features such as pits, fractures, and collapsing cliffs indicate that 67P evolves over time, shedding mass and rearranging its surface morphology. Modelling suggests that tens of meters of material can erode each perihelion pass, meaning a comet is constantly remaking itself over relatively short timescales. One of the most intriguing insights from comet studies is the diversity of water isotopes. The ratio of deuterium to hydrogen D, H, in cometary water is highly variable. For 67P, this ratio is about 3 times higher than Earth's oceans, whereas comets from the Jupiter family, such as 103P, Hartley 2, have D-H ratios closer to terrestrial values. This suggests that Earth's oceans could have been supplied by multiple reservoirs of icy bodies, including both asteroids and comets, rather than a single source. It also highlights that cometary formation occurred in different regions of the early solar nebula, under varying temperature and chemical conditions. Comets are not confined to the solar system's outskirts. Interstellar visitors, such as 2-1 Borisov, discovered in 2019, exhibit volatile activity similar to solar system comets, with carbon monoxide and water sublimating as they approach their star. This indicates that the processes shaping comets' volatile sublimation, jet formation, surface evolution are universal, not unique to our Sun's family. Such observations provide a tantalizing glimpse into the chemistry of other star systems and the possibility that prebiotic molecules are widespread in the galaxy. Their physical and chemical complexity also challenges the old notion of comets as simple snowballs. Many comets are structurally layered, with regions of compacted dust alternating with ice-rich strata, reflecting episodic accretion and heating events in the early solar system. Thermal modeling shows that some layers can survive multiple solar passes, protecting trapped gases and organics for billions of years. In addition, the presence of silicate minerals and refractory materials implies that comets incorporated material from both the inner and outer regions of the protoplanetary disk, making them hybrid records of solar system chemistry. Beyond science, comets are practical subjects of study. Understanding their structure and behavior informs planetary defense strategies, as their loosely bound surfaces and volatile-driven activity make predicting trajectories and impact outcomes more complex than for solid asteroids. Missions like ESA's Comet Interceptor, planned for launch in the mid-2022, aim to study dynamically new comets entering the inner solar system for the first time, offering a fresh perspective on pristine material from the solar system's formation. Meteors don't always burn up. Meteors have fascinated humans for millennia, often inspiring myths and omens, but their true significance is grounded in science. The small streaks of light we call shooting stars are merely the visible phase of meteoroids entering Earth's atmosphere. Most of these objects are no larger than a pebble and burn completely, but a surprising number survive the fiery journey to become meteorites fragments that can reveal the very building blocks of the solar system. A meteoroid begins as debris orbiting the Sun, ranging from dust-sized grains to boulders hundreds of meters across. When a meteoroid strikes Earth's atmosphere, it encounters air at hypersonic speeds, anywhere from 11 kilometers per second for near-Earth objects barely faster than Earth's escape velocity, to as fast as 72 kilometers per second for retrograde interplanetary debris. This rapid compression of air produces extreme heating, often thousands of degrees Celsius, causing the meteoroid's surface to ablate. Despite this, the interior can remain surprisingly intact, especially for dense, metal-rich bodies. The heat and pressure create a fusion, crust a thin, often blackened shell that shields the interior. These crusts can preserve minerals and isotopic ratios unchanged for over 4.5 billion years. Meteorites can be as small as a few grams or as massive as the Hoba meteorite in Namibia, which weighs roughly 60 tons and is estimated to have fallen around 80,000 years ago. Hoba is the largest known intact meteorite on Earth and is almost entirely iron, with about 82% iron and 16% nickel. Meteorites are classified into three broad groups based on their composition. Stony meteorites, which account for about 94% of observed falls, are primarily silicate minerals and often contain chondrule spherical inclusions formed in the solar nebula. Carbonaceous chondrites are a rare subclass that contain water-bearing minerals, amino acids, and complex organic molecules. Iron meteorites, making up roughly 5% of falls, are remnants of differentiated planetary cores, often containing nickel-iron alloys and Widman-Stetton patterns that reveal slow cooling over millions of years. Stony iron meteorites, less than 1% of falls, combine silicate minerals with metal, likely from the boundary zones between cores and mantles of parent bodies. Some meteorites carry materials older than the Sun itself. Prosolar grains, tiny mineral fragments embedded within meteorites, have isotopic compositions that indicate formation in supernovae or red giant stars. These grains survive the collapse of the solar nebula, accretion into meteoroids, and billions of years of cosmic travel before landing on Earth. Not all meteorites arrive quietly. Some meteoroids explode in the atmosphere, releasing enormous energy. The Chelyabinsk event of February 2013 involved a 20-meter object traveling at roughly 19 kilometers per second. It exploded 30 kilometers above the city, releasing energy equivalent to 500 kilotons of TNT, roughly 30 times the Hiroshima atomic bomb. Over 1,500 people were injured, mostly from shattered glass, yet fragments of the meteorite still fell to the ground, weighing a few kilograms each. Carbonaceous chondrites contain water and organic compounds, indicating their presence in the early solar system. Iron meteorites contain features that reveal how cores and mantles separated in early protoplanets. Even tiny micrometeorites, which constantly rain down on Earth at an estimated rate of 40,000 tons per year, help scientists study interplanetary dust, atmospheric entry processes, and solar system evolution. Meteorites also vary in their exposure to cosmic rays, which can be measured through isotopic dating techniques. By analyzing isotopes such as aluminum-2,6 and chlorine-3,6, researchers can determine how long a meteoroid traveled through space before landing, often revealing journeys of millions to hundreds of millions of years. Some rare meteorites, like those originating from the Moon or Mars, provide samples of other worlds without the need for expensive robotic or crewed missions. For example, the Allen Hills 84001 meteorite from Mars contains carbonate globules that preserve ancient aqueous chemistry. Antarctic meteorites, preserved in ice for thousands of years, allow scientists to study extremely delicate compounds and isotopes without contamination. Similarly, desert meteorites, slowly weathered by wind and sun, provide information about surface alteration and cosmic ray exposure. The Kuiper Belt isn't empty. The Kuiper Belt is more than just a distant ring of icy rocks. It is a dynamically rich, evolving region that has profound implications for the architecture and history of our solar system. While it was once considered merely a repository for Pluto-like objects, surveys using the Hubble Space Telescope, the Canada-France-Hawaii Telescope, and more recently, wide-field surveys such as the Outer Solar System Origins Survey, or OSOS, have identified thousands of Kuiper Belt objects, or KBOs, ranging in diameter from tens of kilometers up to more than 2,300 kilometers in the case of Eris. The total population of KBOs is estimated to exceed 500,000 objects larger than 100 kilometers, with millions of smaller fragments, making it a dense region in relative terms, though still spread over a volume nearly 100 times the volume of the inner solar system. The Kuiper belt is divided into several dynamical classes. Classical KBOs, sometimes called Cube-1os, after the prototype 1992 QB1, have relatively stable, low eccentricity orbits between 42 and 48 AU. Resonant KBOs are trapped in mean motion resonances with Neptune, like Pluto in the 3:2 resonance, which protects them from close encounters with the planet. Scattered disk objects, on the other hand, have highly elliptical orbits that can take them hundreds of AU from the Sun, influenced by past interactions with Neptune. Detached objects, like Sedna and 2012 VP 113, have extreme orbits with perihelia well beyond Neptune's reach, hinting at past perturbations by a massive, unseen body or stellar encounters in the Sun's birth cluster. Spectroscopy has revealed that KBOs contain ices of methane, nitrogen, carbon monoxide, and water, as well as complex organics called tholins, which form when sunlight and cosmic rays interact with simpler molecules. For example, Make's bright surface is dominated by methane ice, while Quao has a thin veneer of crystalline water ice mixed with ammonia and methane. Some KBOs, like Haumea, show evidence of past collisions. Haumea's rapid rotation and elongated shape indicate such events, while its collisional family demonstrates that fragments were ejected into the belt long ago. Roughly 10% of KBOs are binaries, with two objects of similar size orbiting a common center of mass. These systems, such as the binary pair of 1998 WW31, provide insight into the low-velocity accretion environment of the early solar system. Contact binaries like Arakoth, visited by New Horizons in 2019, demonstrate that gradual coalescence dominated over catastrophic collisions in the formation of small planetesimals. Arakoth's two lobes, each roughly 15 and 9 kilometers across, joined with minimal disruption, preserving surface features and layers formed as it accumulated dust and ice. The current orbits of resonant and scattered KBOs suggest that Neptune migrated outward by several AU after its formation. Models such as the NICE model propose that interactions between the giant planets caused a rearrangement of the outer solar system, scattering KBOs into the scattered disk and beyond. The clustering of extreme detached objects, like Sedna and 2012 VP 113, has led researchers to hypothesize a potential Planet 9 hypothetical world 5 to 10 times Earth's mass orbiting hundreds of AU from the Sunday. Temperature and solar radiation in the Kuiper belt are extreme. Surface temperatures average around 220 degrees Celsius, cold enough to keep volatiles frozen for billions of years. Solar flux at 40 AU is only about 0.06% of what Earth receives. Yet even this small amount of energy drives sublimation on the brightest KBOs, slowly reshaping their surfaces over eons. Micrometeoroid impacts, cosmic rays, and ultraviolet irradiation further modify their surfaces, creating a patchwork of fresh and irradiated regions that reflect a complex interplay of age, exposure, and chemical composition. Collisions in the Kuiper belt, while infrequent due to the vast distances, can generate debris, contributing to the population of short-period comets. Jupiter family comets are thought to originate primarily in the Kuiper belt, migrating inward over millions of years. Some KBOs, like Pluto, exhibit geological activity driven by internal heat, possibly from radioactive decay, tidal forces, or past impacts, including processes of differentiation, convection, and resurfacing. The Kuiper belt contains objects ranging from small icy fragments to dwarf planets larger than Mercury. These objects preserve primordial materials from the solar nebula and display a wide range of compositions, dynamical behaviors, and size distributions. The Oort cloud is more than a theory. The Oort cloud is often imagined as a distant, icy fog at the edge of the solar system, but it is much more than a speculative concept. Current estimates suggest it contains trillions of objects ranging from a few kilometers to tens of kilometers in diameter, collectively holding a mass possibly several times that of Earth. These icy bodies are primarily composed of water, methane, ammonia, and carbon monoxide ices, along with dust and rock. Though individually tiny and extremely faint, together they form a massive spherical envelope surrounding the Sun, stretching from roughly 2000 AU, the inner Oort cloud, also called the Hills cloud, out to 100,000 AU, nearly halfway to the nearest stars. The formation of the Oort cloud is tied directly to the early evolution of the solar system. During the first 100 million years, the giant planets Jupiter, Saturn, Uranus, and Neptune gravitationally scattered icy planetesimals outward. Many were ejected entirely into interstellar space, but some were captured into distant orbits that eventually formed the Oort cloud. Simulations suggest that roughly 1/10% of the icy bodies originally formed in the giant planet region ended up in the Oort cloud, while the rest either remained in the Kuiper belt, were incorporated into planets, or were lost to interstellar space. The structure of the Oort cloud is often described in two parts. The inner cloud, spanning roughly 2,000 to 20,000 AU, is more tightly bound to the Sun and may contain hundreds of billions of bodies. The outer cloud, from 20,000 to 100,000 AU, is loosely bound and forms a near-spherical halo. Gravitational perturbations from passing stars, molecular clouds, and the Milky Way's tidal forces constantly nudge these icy bodies, occasionally sending them toward the inner solar system as long-period comets. Some of these comets, like Comet Hale-Bopp, take 2,500 to over 10,000 years to complete a single orbit, appearing from random directions and with orbits that can be inclined at any angle. The isotopic compositions, orbital inclinations, and perihelion distributions of long-period comets fit predictions from Oort's model. A statistical survey of 400 long-period comets shows a roughly isotropic distribution of incoming trajectories, which is inconsistent with origins confined to the ecliptic plane or the Kuiper belt. The discovery of Sedna and 2012 VP-113, both detached trans-Neptunian objects with perihelia well beyond Neptune, indicates the presence of a massive distant reservoir influencing their orbits. Occasionally, the Oort cloud may capture material from outside the solar system. Interstellar objects like 1I, Oumuamua, in 2017, and 2I, Borisov, in 2019, demonstrate that material ejected from other stars can travel through space and potentially become gravitationally bound to a star system. Models indicate that a fraction of Oort cloud bodies could be extrasolar in origin, originating from planetary systems located hundreds or thousands of light years away. Temperature and environmental conditions in the Oort cloud are extreme. At distances of 10,000 AU or more, sunlight is about 1 million times weaker than on Earth, so surface temperatures drop to just a few degrees above absolute zero. Cosmic rays and galactic ultraviolet radiation slowly process the ices over billions of years, creating complex organic molecules and dark crusts. Unlike comets in the inner solar system, Oort cloud objects remain largely unaltered, making them time capsules of the primordial solar nebula. Although direct observation is currently impossible with existing telescopes, new technologies and surveys may provide the first glimpses. The Vera C. Rubin Observatory, with its 8.4-meter mirror and 3.2 gigapixel camera, will repeatedly image large areas of the sky, enabling detection of faint, slowly moving objects billions of kilometers away. Space missions like the proposed Interstellar Probe could one day reach the inner Oort cloud, sampling material that has been frozen since the birth of the solar system 4.6 billion years ago. The Oort cloud also influences the solar system dynamically. Its icy bodies serve as a reservoir for long-period comets, contributing to the population of near-Earth objects and occasionally impacting Earth. While impacts from Oort cloud comets are rare, once every tens of thousands of years, their size and velocity can produce catastrophic consequences. Studying these objects is therefore important, not only for planetary science, but also for understanding long-term impact risks. The Oort cloud is the largest, most distant structure gravitationally bound to the Sun, containing primordial ices and organic materials. It is a source of long-period comets that occasionally enter the inner solar system, and its outer regions mark the transition between the Sun's gravitational influence and the surrounding galaxy. Planets aren't perfectly aligned. The apparent order of the solar system masks a surprising level of dynamism and irregularity. Beyond the inclinations and eccentricities of planetary orbits, there are additional layers of complexity caused by resonances and migration. Orbital resonances occur when two or more bodies exert regular gravitational influence on each other, locking their motions into simple ratios. For instance, Jupiter and Saturn have a near 5:2 resonance, meaning that for every 5 orbits Jupiter completes, Saturn completes roughly 2. This resonance has profound consequences, subtly shaping the positions of asteroids in the main belt and affecting the stability of orbits across the system. Models of planetary formation, such as the NICE model, suggest that the giant planets didn't form in their current locations. Instead, Jupiter, Saturn, Uranus, and Neptune moved through the protoplanetary disk, scattering icy bodies and smaller planetesimals. This movement tilted orbits, formed the asteroid belt, and sent material into the inner solar system, delivering water and organics to early Earth. Neptune's outward migration likely trapped many Kuiper belt objects in resonant orbits, explaining why Pluto is in a 3:2 resonance with Neptune. Inclination isn't uniform across all planets. Mars tilts about 1.85 degrees relative to the ecliptic, while Venus tilts 3.4 degrees with retrograde rotation. Uranus has an axial tilt of 98 degrees, lying nearly on its side. Uranus experiences 4 two-year-long summers and winters at each pole, while Earth's 23.5 degrees axial tilt produces seasonal cycles. Even minor tilts in Mercury and Venus contribute to gravitational interactions, perturbing the orbits of nearby bodies over millions of years. Mercury's eccentric orbit creates a perihelion shift of 43 arcseconds per century, a discrepancy that helped confirm Einstein's theory of general relativity. Pluto's orbit, with an eccentricity of 0.25, takes it from 29.7 AU at perihelion to 49.3 AU at aphelion. Its 17 degrees inclined orbit means that Pluto spends a significant fraction of its 248-year orbit above or below the plane where most planets travel. Many small bodies, including asteroids and dwarf planets, occupy highly inclined orbits, with some exceeding 30 degrees relative to the ecliptic. Trans-Neptunian objects like Sedna have perihelia at 76 AU and aphelia extending over 900 AU, on orbits tilted 11 degrees relative to the ecliptic. These trajectories result from gravitational interactions with giant planets, passing stars, or potentially unseen massive objects in the outer solar system. Planetary precession is another subtle but important phenomenon. Over tens of thousands of years, gravitational torques from the Sun, Moon, and other planets slowly rotate the orientation of orbital ellipses. For Earth, this manifests in Milankovitch cycles, which vary orbital eccentricity, axial tilt, and precession to produce long-term climate changes. Jupiter and Saturn's mutual interactions produce similar precessions, influencing asteroid belts and long-period comet orbits. Even tiny variations in Neptune's orbit ripple outward, affecting distant Kuiper belt and Oort cloud bodies. Simulations indicate that Mercury's orbit is particularly sensitive. There is a small but non-zero chance, around 1%, that it could destabilize over the next 5 billion years, possibly leading to orbital crossing or collisions with Venus or the Sunday. Moons and planetary rings add three-dimensional complexity. Jupiter's Galilean moons Io, Europa, Ganymede, and Callisto orbit in nearly the same plane, but their slight inclinations and resonances drive tidal heating and geological activity, such as Io's volcanoes and Europa's subsurface ocean. Saturn's rings, tilted at 26.7 degrees relative to its equator, create seasonal illumination patterns, while Uranus's rings follow its axial tilt, producing shadows and light variations over decades. Distances are bigger than they seem. Textbooks often show the planets lined up neatly, each orbit evenly spaced from the Sunday. Mercury, Venus, Earth, Mars, Jupiter, and the rest are illustrated in simple concentric rings, as if the solar system were a tidy clockwork model. Reality, however, is far less orderly and far more empty. The distances between planets are staggering, and our minds struggle to grasp their immensity. Astronomers use the astronomical unit AU, the average distance between Earth and the Sun, about 150 million kilometers. Mercury orbits at 0.39 AU, Venus at 0.72 AU, Earth at 1 AU, and Mars at 1.52 AU. The asteroid belt lies between Mars and Jupiter, spanning roughly 2.1 to 3.3 AU. Jupiter orbits at 5.2 AU, Saturn at 9.6 AU, Uranus at 19.2 AU, Neptune at 30.1 AU, and Pluto at an average of 39.5 AU. Pluto's orbit is highly elliptical, ranging closer to or farther from the Sun over its 248-year orbit. Scaled models can help visualize distances. If the Sun were the size of a basketball, Earth would orbit about 26 meters away, Neptune nearly 800 meters, and Pluto over 1 kilometer. The outer solar system stretches this concept to near incomprehensibility. Beyond Neptune lies the Kuiper Belt, a region containing hundreds of thousands of icy objects and dwarf planets like Haumea, Makemake, and Eris, extending from roughly 30 to 55 AU. And farther still, the hypothetical Oort cloud may stretch up to 100,000 AU, nearly 1 light-year from the Sunday. This means that even the most distant edges of the Sun's gravitational influence are still only a fraction of the distance to the nearest stars, highlighting how isolated our solar system truly is. Sunlight takes 8 minutes and 20 seconds to reach Earth, 1 hour and 20 minutes to reach Saturn, about 2 hours and 40 minutes to Uranus, and over 4 hours to Neptune. Signals from Voyager 1, launched in 1977, take over 22 hours to reach Earth. Voyager 1 is currently over 160 AU from the Sunday. Voyager 2, launched later, is also exploring the interstellar boundary, providing measurements of the heliosphere's outer limits. A journey from Earth to Mars averages 225 million kilometers, depending on orbital positions. Spacecraft must follow precise interplanetary trajectories, often using gravity assists to conserve fuel. The Mars Science Laboratory, carrying the Curiosity rover, traveled over 567 million kilometers along a curved trajectory to reach Mars. The sheer scale also affects timing. Communication delays are unavoidable, which means mission operators must plan maneuvers in advance. Commands to the Mars rovers take anywhere from 4 to 24 minutes to arrive, depending on planetary positions, requiring autonomous navigation systems to handle real-time adjustments. The vast distances also impact spacecraft design, dictating fuel requirements, power systems, and thermal control for the extreme environments encountered en route. Most of the solar system's volume is empty, with planets, moons, asteroids, and comets occupying small regions. Collisions between planets are extremely rare. Within the asteroid belt, objects are separated by millions of kilometers on average. This vastness also affects our perception of planetary motion. When we look up at the night sky, stars appear fixed, and planets move slowly against this backdrop. In reality, those apparent movements are occurring over immense distances and at tremendous speeds. Earth travels around the Sun at about 30 kilometers per second, Jupiter at 13 kilometers per second, and Neptune at 5.4 kilometers per second. Yet the visual change in position is subtle because the backdrop of space is so immense that even rapid motion appears gradual. Long-period comets originate in the Oort cloud. They can take thousands to millions of years to complete a single orbit around the Sunday. Gravitational perturbations from passing stars or galactic tides can send these comets into the inner solar system. Spacecraft traveling to Mars, the asteroid belt, or the Kuiper belt must carry sufficient fuel, withstand cosmic radiation, and maintain operational systems for years or decades. Distances in space are a critical engineering constraint for mission planning. The solar system is not static. It's tempting to imagine the solar system as a perfectly ordered clockwork mechanism, planets orbiting the Sun in neat ellipses, while the central star itself remains stationary. This comforting picture, though convenient for diagrams, misses the astonishing dynamism of our cosmic neighborhood. In reality, the solar system is far from static. Every object within it moves, wobbles, and shifts over time, governed by the invisible hand of gravity and the subtle influences of neighboring stars and interstellar material. To begin with, the Sun itself is not stationary. Like all stars in the Milky Way, it orbits the galactic center at roughly 220 kilometers per second, completing a full rotation every 230 million years. The solar system travels with it, bound together by the Sun's gravitational field, sweeping through interstellar space at extraordinary speeds. This means that, although planets appear to orbit a stationary Sun on human timescales, the entire system is moving collectively through a galaxy brimming with stars, gas clouds, and dark matter. Even in the local frame of the Sun, there is subtle motion. The Sun is not a fixed anchor. Its position responds to the gravitational tug of the planets. Jupiter, the most massive planet, exerts the strongest influence, followed by Saturn. The result is a solar wobble, which shifts the solar system's barycenter, the center of mass, around which all objects orbit, sometimes just outside the Sun's surface. In effect, the Sun orbits this shifting point too, moving slightly in response to its planetary companions. This barycentric motion is so precise that astronomers use it to detect distant exoplanets around other stars, as the wobble produces measurable Doppler shifts in starlight. Planets themselves are far from immutable. Their orbits change slowly over time due to mutual gravitational interactions, collisions, and even the cumulative effect of tiny forces such as solar radiation and interstellar drag. For example, Earth's orbital eccentricity fluctuates between nearly circular 0.003 and mildly elliptical 0.058 over 100,000-year cycles, while its axial tilt varies between 22.1 degrees and 24.5 degrees over roughly 41,000 years. These changes drive long-term climate cycles known as Milankovitch cycles. Mars experiences even larger swings, with obliquity varying from 15 degrees to 35 degrees over hundreds of thousands of years. The outer planets demonstrate even greater mobility over astronomical timescales. Studies of planetary migration indicate that the gas giants did not always occupy their current positions. After the Sun's formation, gravitational interactions with the protoplanetary disk caused Jupiter to migrate slightly inward by about 0.2 AU, while Saturn, Uranus, and Neptune drifted outward a process described in the Nice model of planetary evolution. These shifts were not minor. The movements of the giants likely destabilized smaller bodies in the early solar system, scattering material to form the Kuiper belt and populating the distant Oort cloud. The migration may also explain Neptune's 2 to 3 orbital resonance with Pluto and other trans-Neptunian objects, locking some bodies into stable orbits despite billions of years of motion. Even the asteroid belt is far from a static collection of rocks. Gravitational resonances with Jupiter clear gaps, known as Kirkwood gaps, while collisions continually break apart and reform asteroids, creating families of fragments sharing similar orbits. Thermal effects, like the Yarkovsky effect, can gradually shift small asteroids' orbits over millions of years. This effect occurs because rotating asteroids absorb sunlight and re-emit it as heat, producing a minuscule but continuous thrust. Over time, these tiny nudges can move asteroids into Earth-crossing orbits, producing potential meteorite falls and sometimes even impacting our planet. Comets are equally affected by motion on a grand scale. Long-period comets from the Oort cloud enter the inner solar system due to gravitational disturbances, which can be caused by passing stars, molecular clouds, or galactic tidal forces. One of the most striking future examples is Gliese 710, a star expected to pass within 0.2 light-years of the Sun in approximately 1.3 million years. At such proximity, it could perturb a large number of Oort cloud objects, sending comets inward towards the inner solar system. Moreover, the solar system's motion is not confined to translations and orbital shifts. The entire structure exhibits subtle oscillations relative to the galactic plane. As the Sun travels around the Milky Way, it oscillates up and down across the galactic disk with a period of roughly 60 million years. These vertical motions may influence the influx of comets from the Oort cloud, potentially triggering periodic increases in impact events on Earth. Even smaller effects accumulate over time. Micrometeoroids and interstellar dust slowly alter planetary and satellite surfaces. Tidal interactions between moons and planets, such as between Earth and the Moon, gradually change rotational periods. The Moon recedes from Earth at about 3.8 centimeters per year, subtly altering Earth's rotation and lengthening our days over millions of years. Motion in the solar system operates on every scale, from tiny grains of dust to the largest planets. Orbits shift, positions migrate, and gravitational influences affect objects from the smallest asteroid to the largest gas giant. The Sun's position changes in response to planetary gravitational pulls, while the entire solar system moves at hundreds of kilometers per second through the galaxy. Planetary orbits change over time due to gravitational interactions and other forces. Comet paths are influenced by passing stars and galactic tides, and planets continue to drift within the solar system as part of a gravitationally interconnected system. The heliopause isn't a hard wall. Many people imagine the heliopause as a solid, well-defined wall, the cosmic edge of the solar system. The idea of a rigid boundary separating our Sun's domain from interstellar space is compelling, but it is far from accurate. In reality, the heliopause is a diffuse, dynamic frontier, a transitional zone where solar forces gradually yield to the galactic environment. It is not a wall, it is a vast, shifting region shaped by both the Sun and the galaxy around it. To understand this boundary, we first need to examine the solar wind. The Sun constantly emits a stream of charged particles, mainly protons and electrons, flowing outward at speeds ranging from 300 to 800 kilometers per second. This plasma doesn't just travel through empty space, it carries the Sun's magnetic field along with it, creating a bubble known as the heliosphere. The heliosphere stretches far beyond the outer planets over 100 astronomical units from the Sun, creating a magnetic cocoon that shields the solar system from much of the galaxy's high-energy cosmic rays. The heliopause is the region where the pressure of the outward-flowing solar wind balances the pressure of the interstellar medium, a tenuous mix of gas, dust, and magnetic fields that permeates the space between stars. This transitional zone extends over tens of AU, where particle densities, temperatures, and magnetic field directions change gradually. NASA's Voyager spacecraft provided the first direct measurements of this region. Voyager 1 crossed the heliopause on the 25th of August 2012 at approximately 121 AU from the Sunday. Voyager 2 followed on the 5th of November 2018 at around 119 AU. The spacecraft recorded a complex environment. Plasma densities increased, magnetic field orientation shifted, and energetic particles from the solar wind decreased while interstellar particles became more dominant. The heliopause expands and contracts with the Sun's activity cycle. During solar maximum, when the Sun emits a stronger, more turbulent solar wind, the heliosphere swells outward. During solar minimum, when solar activity weakens, the heliosphere contracts. Modeling suggests that at its closest contraction, the boundary may approach 115 AU, while during strong solar activity, it can extend beyond 125 AU. Interestingly, the heliopause is not perfectly spherical. Voyager data, along with observations from the Interstellar Boundary Explorer, or IBEX, indicate that the heliosphere is asymmetrical, influenced by the Sun's motion through the galaxy and by the orientation of local interstellar magnetic fields. The Sun moves at about 26 kilometers per second relative to the local interstellar medium, causing the heliosphere to compress in the direction of motion, the nose, and stretch out into a long tail in the opposite direction. Some models describe its shape as a croissant rather than a bubble, with the trailing heliotail extending thousands of AU downstream. The heliopause is also shaped by the interaction of different particle populations. Inside, the plasma is dominated by charged particles from the Sun, while outside, galactic cosmic rays and interstellar plasma prevail. In the transition zone, particles from both environments intermingle, creating turbulence and fluctuating magnetic fields. IBEX observations reveal energetic neutral atoms streaming back into the inner solar system from this region, providing a global map of heliospheric boundaries and showing that the transition zone is both porous and dynamic. The heliopause deflects much of the galaxy's high-energy cosmic radiation, shielding planets, spacecraft, and the outer reaches of the solar system from high-energy particles. Voyager 1 recorded particle fluxes rising by more than 70% after crossing the heliopause compared to levels inside the heliosphere. The heliopause is influenced not only by solar and interstellar pressures, but also by external perturbations. Passing stars, interstellar clouds, and molecular gas filaments can compress or distort the boundary. Nearby star-forming regions, like the Scorpius-Centaurus Association, may generate local variations in interstellar pressure that nudge the heliopause, changing its shape and particle fluxes over tens of thousands of years. Voyager measurements have revealed magnetic islands and knots in the transition zone regions where the solar and interstellar magnetic fields reconnect. These reconnection events release bursts of energy and accelerate particles, creating a complex, turbulent environment rather than a calm, static boundary. The heliopause is shaped by the Sun's activity, the flow of the solar wind, the pressure of the interstellar medium, and the Sun's motion through the galaxy. It moves and shifts, representing the transition where the Sun's sphere of influence decreases and interstellar space begins, with solar and galactic forces interacting. The heliosphere extends far beyond Pluto or the Kuiper belt, with its outer boundary hundreds of times farther than the Earth-Sun distance. Voyager observations show that the Sun's influence extends into a turbulent region where its forces gradually yield to those of the Milky Way. It is a dynamic, shifting, turbulent zone where solar and interstellar space intermingle. Particle flows, magnetic reconnections, and varying pressures characterize this transitional region, marking the threshold between the Sun's influence and interstellar space. Pluto's demotion confuses reality. In 2006, Pluto's reclassification from planet to dwarf planet shocked the public. Headlines framed it as a dramatic demotion, sparking petitions, protests, and an endless stream of memes demanding its reinstatement. The decision followed new discoveries in the outer solar system and the adoption of a formal definition of a planet by the International Astronomical Union. The context begins with the early 21st century surge in discoveries beyond Neptune. For decades, Pluto was the ninth planet, orbiting quietly in the outer solar system. But in 2005, astronomers at the Palomar Observatory in California discovered Eris, a distant icy world approximately 2,326 kilometers in diameter, slightly smaller than Pluto's 2,377 kilometers. Eris's discovery, along with Haumea, which measures about 1,632 kilometers, and Makemake, roughly 1,434 kilometers across, revealed a growing population of bodies rivaling or exceeding Pluto in size. If Pluto retained planetary status, dozens of similar objects in the Kuiper Belt might demand the same title, making the solar system more crowded than textbooks could reasonably depict. This prompted the International Astronomical Union to formalize the definition of a planet. According to the IAU, a planet must orbit the Sun directly, have sufficient mass for self-gravity to form a nearly round shape, and have cleared its orbital zone of other debris. Pluto satisfies the first two conditions. It orbits the Sun every 248 Earth years, and is massive enough for its gravity to shape it into a nearly spherical body. The problem arises with the third criterion. Pluto shares its orbital neighborhood with a vast collection of icy objects in the Kuiper Belt, ranging from a few kilometers across to hundreds of kilometers, creating a crowded orbital environment. By this measure, Pluto had not cleared its path and thus could not meet the IAU's definition. The new category, dwarf planet, was established to classify bodies that are massive enough to be nearly round but have not cleared their orbits. Ceres, the first dwarf planet identified in 1801 within the asteroid belt, joins Pluto, Eris, Haumea, Makemake, and a growing list of bodies as examples of this classification. Estimates suggest that the Kuiper Belt may contain hundreds or thousands of other dwarf planets, most yet undiscovered. NASA's New Horizons mission indicates that there is evidence of cryovolcanism, or ice volcanoes, and a complex, layered atmosphere containing nitrogen, methane, and carbon monoxide in Pluto. The mission also refined our understanding of Pluto's size, mass, and density. Its diameter, 2,377 kilometers, is slightly smaller than initially estimated, while its mass, 1.31 times 10, 22 kilograms, indicates a density of about 1.86 grams per cubic centimeter, suggesting a mix of rock and ice. Pluto's largest moon, Charon, is enormous relative to Pluto itself. Together, Pluto and Charon form a binary system, orbiting a common barycenter located outside Pluto's surface, a feature unique among the solar system's dwarf planets. Pluto and other dwarf planets in the Kuiper Belt are remnants of the early solar nebula, preserved in a frozen state for over 4.5 billion years. Studying them provides information on how planets form, migrate, and interact with smaller bodies over time. Astronomers are discovering numerous small worlds orbiting stars in other systems. Distinguishing between dominant planets and smaller bodies allows for classification consistent with definitions used in the solar system. The discovery of distant Pluto-like objects such as Sedna, with a perihelion of 76 AU and 2014 UZ 200 and 24 dd, orbiting at roughly 92 AU, highlights the population of objects in the outer solar system and the ongoing study of their orbital characteristics. Ceres transitioned from planet to asteroid to dwarf planet over 2 centuries. Pluto's reclassification reflects changes in planetary definitions as astronomers incorporate new observations and discoveries. Pluto's surface features include icy plains, mountains, glaciers, and the Sputnik Planitia Basin. Pluto and Charon form a binary system with a barycenter outside Pluto's surface. Dwarf planets and Kuiper belt discoveries are being studied through ongoing surveys from telescopes such as Pan-STARRS and the Vera Rubin Observatory. These surveys continue to expand knowledge of the outer solar system. NASA images aren't just pictures. Images from the Hubble Space Telescope, the James Webb Space Telescope, or planetary missions like Juno and Perseverance often captivate the public. Nebulae glow in vibrant reds and blues, galaxies spiral in iridescent patterns, and planets shimmer with surreal clarity. It's easy to assume these images are direct snapshots of reality, but that assumption is misleading. Most of what we see in these iconic images is a carefully constructed visualization of scientific data rather than true color photography. Space telescopes do not capture light like a conventional camera. They collect photons across a range of wavelengths, many beyond human perception, including ultraviolet, infrared, X-ray, and even radio waves. Hubble, for instance, can observe from 115 nanometers in the ultraviolet to 2,500 nanometers in the near-infrared, while JWST extends deep into the mid-infrared, from about 600 nanometers to 28 micrometers. Since human eyes detect only wavelengths from roughly 400 to 700 nanometers, astronomers must assign visible colors to these data to interpret them. This process creates false color or representative color images, translating invisible information into visual cues. The assignment of color is systematic and meaningful, not arbitrary. In JWST's infrared imagery, shorter wavelengths are often mapped to blue, medium wavelengths to green, and longer wavelengths to red. This mapping highlights temperature differences, chemical composition, and density variations in celestial objects. A young star embedded in a dusty nebula may appear blue in such an image because it emits higher energy infrared radiation, while cooler dust and gas glow red. These visualizations allow scientists to discern features that would otherwise remain invisible, such as shock fronts, ionization zones, or areas of star formation. Planetary spacecraft employ similar methods. Raw images sent from Mars rovers like Perseverance or orbiters like Juno are frequently grayscale or muted in color due to sensor limitations and the spectral sensitivity of the cameras. Light scattering, atmospheric dust, and solar illumination angles can make surfaces appear dramatically different than they would under normal daylight. Scientists apply calibration to correct brightness, adjust contrast, and balance colors to approximate the object's appearance to human eyes, while preserving the accuracy of surface features and material compositions. Sometimes, the images are composites, combining multiple filters or exposures. Hubble's Pillars of Creation photograph, captured in the Eagle Nebula, uses several filters sensitive to hydrogen, sulfur, and oxygen emissions. Each filter corresponds to a distinct chemical element, producing separate grayscale images that are later combined into a color composite. Hydrogen is often assigned red, sulfur green, and oxygen blue. This process encodes the chemical and physical properties of the nebula, revealing structures and interactions that are invisible in ordinary light. Multispectral imaging extends beyond aesthetics. By capturing light across multiple wavelengths, astronomers can detect variations in temperature, ionization, magnetic fields, and elemental abundance. JWST, for instance, can identify molecules such as water vapor, carbon dioxide, methane, and carbon monoxide in exoplanet atmospheres by analyzing infrared absorption patterns. When this spectral information is translated into color-coded images, scientists can visualize phenomena like hotspots, dust rings, or shockwaves, effectively turning raw data into a tangible representation. Even solar system images rely on interpretation. Saturn's rings, observed by Cassini, show a range of colors representing differences in particle composition and size. Bright regions reflect icy material, while darker streaks indicate rocky or organic rich particles. Similarly, images of Jupiter's Great Red Spot or the swirling bands of its atmosphere are processed to enhance contrast and clarify cloud features, revealing patterns and vortices that are crucial for understanding the planet's meteorology. Processing images is essential for scientific measurement. JWST's deep field images combine multiple long exposures totaling tens of hours, sometimes across different wavelengths. These exposures are corrected for instrumental effects, cosmic rays, and detector noise. By stacking and color mapping the data, faint galaxies billions of light years away become visible, allowing astronomers to study their morphology, star formation rates, and chemical compositions. Image processing does not falsify data. NASA states that adjustments convey information that cannot be directly perceived. A photo of the Carina Nebula in infrared may show red and green swirls, which encode measurements of temperature, density, and chemical composition. Exoplanetary images often involve subtracting stellar glare, enhancing faint signals, and translating spectral readings into visual form. Images of the Crab Nebula or the Whirlpool Galaxy combine color, brightness, and contrast adjustments to represent specific measurements made by instruments. Astronomers can quantify the energy output of a star-forming region, trace gas flows, and detect distant planets using these visual data. JWST's first deep field observations, revealing galaxies formed 200 million years after the Big Bang, relied on translating infrared data into visual form. Cassini's mosaics of Saturn's polar hexagon revealed wind speeds and cloud structures. Hubble's ultraviolet surveys mapped starburst regions, identifying areas of rapid stellar evolution. These images provide quantitative information on patterns and structures across space and time. We've never explored everything. It's easy to assume that humanity has charted the solar system. After all, we've walked on the moon, sent rovers across Mars, and launched probes past all the major planets. Yet the reality is far more humbling. Despite decades of exploration, most of the solar system remains largely unvisited and unknown. Our achievements are milestones across a vast frontier, not a comprehensive survey. Even our closest neighbor, Mars, is only partially mapped. While orbiters like Mars Reconnaissance Orbiter have produced incredibly detailed imagery, less than 30% of the Martian surface has been mapped at sub-meter resolution. Vast stretches of terrain, including deep canyons, highland plateaus, and ancient riverbeds, have yet to be directly observed at the scales necessary to understand their geology or potential for past life. Rovers like Perseverance and Curiosity explore only a few kilometers at a time, leaving the majority of the planet untouched. The outer planets are even more elusive. Only a handful of spacecraft have ever reached them: Pioneer 10 and 11, Voyager 1 and 2, Galileo, Cassini, Juno, and New Horizons. Of these, Uranus and Neptune have only been visited once. Voyager 2 inches 1,986 and 1,989, respectively. No orbiter has ever remained in orbit around either planet. Much of our knowledge about their atmospheres, internal structures, and magnetic fields comes from brief flybys, yet these two ice giants constitute nearly 99% of the solar system's planetary volume beyond Saturn. Critical questions remain unanswered. Why does Uranus's magnetic field tilt so dramatically from its rotation axis, while Neptune's is so offset from its center? What drives the extreme winds observed on both planets, reaching up to 2,100 kilometers per hour on Neptune? Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies extending from roughly 30 to 55 astronomical units. This population contains thousands of objects larger than 100 kilometers, including dwarf planets like Haumea, Makemake, and Eris. Yet we have visited only one, Pluto, and only for a few hours during New Horizons' 2015 flyby. Even the close encounter revealed surprises: towering mountains of water ice, flowing nitrogen glaciers, and a tenuous atmosphere. The rest of the Kuiper Belt remains largely invisible, appearing in telescopes as faint points of light that cannot yet be resolved into detailed surfaces. The Oort cloud is a hypothesized spherical shell of icy bodies from 2,000 to 100,000 AU. No spacecraft has entered or approached it. Its existence is inferred from the orbits of long-period comets. Even the Sun, the center of our system, holds mysteries. Parker Solar Probe, launched in 2018, has become the first human-made object to enter the Sun's corona, traveling within 6.9 million kilometers of its surface. This region controls the solar wind, space weather, and the magnetic environment that affects every planet. The data Parker gathers on solar particle acceleration, coronal heating, and magnetic reconnection are only now beginning to rewrite our understanding of how stars influence their planetary systems. Solar Orbiter, meanwhile, is capturing the Sun's poles for the first time, providing a view no previous mission could achieve. Asteroids and comets are largely unexplored. NASA's OSIRIS-REx visited asteroid Bennu and retrieved a sample in 2020. The Lucy mission is targeting Trojan asteroids around Jupiter. These missions cover only a small fraction of the millions of small bodies orbiting the Sunday. Many remain unobserved, and their composition, structure, and history are largely unknown. Our telescopic surveys have mapped thousands of objects, but these observations provide only outlines. Even the nearest dwarf planets beyond Pluto are little more than bright points to our instruments, their surface geology, atmospheric conditions, and potential for past or present activity largely uncharted. Beyond them, hypothetical planets or clusters of icy bodies may exist in the outer reaches, unseen and unconfirmed, further emphasizing how little we truly know. Voyager 1 and 2 observed magnetic field structures at the edges of the heliosphere. New Horizons detected geologic activity on Pluto. Juno is studying Jupiter's deep atmospheric currents and polar cyclones. Exploration of the solar system is incomplete. Many regions, including the spaces between planets, the Kuiper Belt, the Oort cloud, and large portions of Mars and the Moon, have been visited only partially or not at all. Knowledge of planets, comets, and the outer solar system is limited, and many regions remain beyond current reach.